No, it is okay. It is okay. I mean, you feel that. I just forget to take the paper for the paper. I agree with you. Thanks.
Okay.
No, testing question.
Nagyon jó, szerintem itt fel fog tűnni mindenkinek.
Neked most az e-mail e-mailből a vége?
Nekem vagy neki?
Nem.
Írófogjába.
Hát azt kértek tényleg, de azért nem fogok elhúzni. Én azt gondoltam, hogy itt maradok, bár nem vagyok.
Mindegy, most dumáljunk már valamikor, mert te is annyira vízi vagy, hogy nem bírsz jönni hozzá, meg én is
Már se indultak a dolgok, de mindig az volt, hogy
Ki nem kapta? A Majoros Balázs nem kapta meg. Ja, mert
aztán valaki eltört talán.
Majros. Szerintem.
jól vagytok.
Elhívta a saját e-mailt.
Igen. Tessék? Ja.
Jaj, konkrétan
Hallasz, Gábor? Én hallak, vagy nem hallok.
Hallak, igen.
Jó, oké, akkor
Szervusz, Lapi. Igen, igen, hol beszéljek? Melyikről megy a mikrofon?
Arról kéne menjen a mikrofon.
Hallod, Balázs?
Jó hallottam.
Erről nem megy ki a csak azt, hogy tudjuk tesztelni, hogy ez egy a
Jó.
YouTube-on kint van a hang.
Jó, most beszélek, nem tudom, hogy mennyi a késés. Nem kéne, hogy sok legyen.
Anybody who has already
Sziasztok!
Most már igen.
Pisti, hallasz minket?
Én igen.
Ó, szuper, mi is hallunk téged.
Oké, szuper. Bocsánat, írtam egy levet, hogy nincs linkem, de kaptam, akkor köszi, itt vagyok.
Oké. De miért?
Ilyet még nem pipáltam. De ilyet még nem láttam. Hello, szia.
Azt én kihúzom, hogy most töltöm a gépemet, ezt kihúzhatom meg, akkor például most is kihúzhatom.
Ez egy HDMI, szuper, akkor igazából.
Lesz vetítve?
Hogy a magát lehetne, hogy a legyen, ki tudod mindent tudod, legyen a és miatt. Ugyan ezt a kamera másik.
Elvileg kipináltam, de meg
Igen, nem kötelező, csak ez mi lesz?
Az majd az előadás.
Ja, az előadás. Jó, oké. Nem gond.
nekem egy előadást csináltam.
Lehet az egész képernyőt, vagy...
Mehet az egész, hát úgyis ezzel az izével játszom. Ebből kikapjuk belőle az izét.
Azt nem menjen az egész, mert azért lehetetlen.
Így? Szuper. Megy, szuper. Okay, welcome everybody. Please take a seat. I would like to have some feedback from outside. That can you hear us?
Én innen jól hallak titeket.
Okay, thank you very much. Please move this because. So welcome everybody. This is the 11th GPU day, and I'm very happy that we can see you all in this nice in-person meeting or a hybrid meeting, but many of you are here. So I would like to open the workshop with a couple of practical things, and I will give the word to Peter Levay, who is the General Director of the Wigner Institute, the main host of our event. So here you see the most useful information. The very useful information can be found here on this flip chart. So most of you could find that the Wi-Fi is Castle Hill and the password is conference with all capital letters. Wearing mask is not compulsory, but it's recommended, so you can have it. Speakers can speak without that because it's much more easier, and of course you can read from the mouse. It's kind of easy way, but as you wish. We will have the coffee breaks at the back. So, but anytime you feel tired or have any other things, you can just have a coffee or drink. It is okay from our side. The lunch will be downstairs. So let me go to here. So you see that we have the gpuday.com. This is the main web page, which direct you to this Indico website, which is also a kind of synchron version of the program here and here. This is the place where I mean, both places we will have the talks, but it depending on the practicity, you will see that which will be the easier or faster. Okay, so and this year we have a couple of interesting topics. Of course, as usual, GPU is not the only device what we are using, but massive parallel programming technologies. And many things which can be related to this one, either the classical parallel computing, GPUs, FPGAs, graphic applications, physical problems, machine learning, and slightly quantum machine learning, which is now available or soon will be available in our laboratory as a quantum computer simulator, which will be presented in the next days. Shortly, some of you who are not familiar with us, so the Wigner GPU Laboratory started in 2009. Mate is one of the founder who is now already in the industry, and we started with a couple of machines. We were dedicated to GPUs only, but later we moved to multi-core and parallel computing, and now we have a group of people who are serving this. If you would like to see the history in brief, a few days ago, 2 years ago, we celebrated the 10th anniversary of the GPU Laboratory, and this is the 11th GPU day, which we are regularly doing every year. So you see that the laboratory was originally made for high energy physics calculation, which is the main motivative or moving force of our group. And ALICE and CMS collaboration has also used that by CERN the facility. And we also have gravitational directions. And that was the time when we really formed the laboratory. And then we started the GPU Day series. And basically, let me jump to this point. So from 2016, we started the GPU Laboratory Fellowships, when some of you could already join us and having fun working on a certain topics. If you go to the web page, you can see the certain physical and other programs where colleagues are contributing to the laboratory and using the laboratory. And the very latest news, this is really just the 1 week fresh hot news, that the Wigner GPU laboratory changed the name to Wigner Scientific Computational Laboratory. We merged together the scientific part of the Wigner Data Center, which is a much more bigger device. And we are part of the top 50 Hungarian national laboratories. So we jump to a slightly higher level starting from now. Okay, so here you see the staff and sitting in the first row. I'm also here, so you can find us during the whole 2 days and ask anything directly, and we will help you to present and guide you through these interesting things. We have many academic and industrial partners, as you can see here, and I really appreciate those who are also here and following us since long time ago, especially from the industrial part, which is very hard since the thinking way and the working methods are completely different in the 2 fields. So I'm very happy if we can find the matching point. Signed out. Gabor, am I okay? Okay. Try to do this. Okay. So we have some results in numbers. So here you see the GPU days participations. Even it's very interesting that in 2020 we had very high attendance. However, we had this hybrid event, and I hope we will get the similar numbers for this year as well. We have ongoing activities with these fellowships and with the partners. We have all 30 plus numbers almost everywhere. Okay, so let me jump to here. So, and let me say a few words and a special thanks to our supporters or who are providing us the opportunity to have this event. Of course, the Wigner Institute, which is feeding us since 10 years, more than 10 years. We have also the Lombik Limited, thank you very much. The Stream HPC, which was started everything from somewhere else by Mate, and of course Ericsson and Technolinks. Yeah, okay. And I really appreciate to support this event. The program is pretty dense, you see here, and I kindly ask all of you who are contributing to try to upload the talk or send us the talk or just give it in a stick in time to have this. And one more thing, that this event now is joined with the AIME event, which is the forthcoming. So we will switch from the GPU day to the AIME event tomorrow at lunchtime, which is also a very interesting. So this academy, artificial intelligence academy industry matching event, which will be a kind of continuation, either similar but slightly different topics. And I think this is the time maybe I give the word to Peter Levai to say something on us. To open the event, please, Peter. Yeah.
Thank you very much, Gergely. My name is Peter Levai, and I am the Director General of the Wigner Research Center for Physics. It is a privilege for me to stand here now 12 times, and I think 12 years is a large time even for a young guys. And now it seems to me that the GPU laboratories start to grow up to the novice status, because 12 years in the life of a workshop series is a serious time. And 12 years ago when we started, we just have the hope that these days will become something like a knowledge transfer event, a continuous possibility to exchange ideas, and what is the main thing, to attract not only the senior colleagues, but also the young colleagues who are just entering into this field and who can find a place where he can meet with the other experts. Also, where he or she can, I am very happy to see also the ladies, he and she can exchange ideas to learn and also to see the future, the near future and the faraway future. So in this sense, I think this GPU Day is a very important event, also important for the Wigner Research Center for Physics. What happened in the center that during these 12 years, so 2 years ago, we have established a new department. This is the Department of Computing Science. What is it? Oh, yeah, sorry. So Computational Physics Department, which now has, because this is simply just the computing, so the computing people. And in that department also, there is a large, how would I say, mixing of the brain researchers and machine human interface and generally other topics connecting to artificial intelligence, machine learning, their application in different fields. So in that sense, so this is one side. The other side, that in both institute, and I am very happy to see colleagues both from the Institute for Particle and Nuclear Physics and Institute of Solid State Physics and Optics. So I think theoretical physics and theoretical investigation demand the latest computer technology, and you cannot miss the opportunity to learn, to see how can you use this newest and newest technological developments. So this is very important for the institute. And now the latest step, just let's say a few days ago, it was acknowledged and it was advertised that one of our open laboratory, so this Wigner Scientific Computing Computational Laboratory, got the certificate to become one of the top 50 national infrastructure. So we are just in the meantime also to make a fancy and attractive web page for that. The final words, I am very happy to stand here to say a few words to you. I wish you a very successful and very fruitful meetings. And the very last words that I would like to thank, first of all, to Gergely Barnaföldi to again organize and, how would I say, orchestrating this event, and what are the real work, the young people, and all of you. First of all, I am very happy to see Ferenc Egri Nagymáté, Egri Nagymáté Ferenc. Ferenc Nagy Egri, okay. And Bíró Gábor and Kacskovics Zsolt and Szabolcs. Szabolcs. Nem, Balázs. I didn't see you in the last year, so you see, so we should meet more times. So thank you very much to giving all of the support and all of the help. And also, if you got interested in these activities and would like to see more from it in the Wigner Research Center, please contact these young and senior guys and you can get more information. And last words, I really appreciate for all of our partners, strategic partners, Lombik and other Ericsson, who supported this event, and I expect that this connection, this partnership will remain alive, because, and not because of friendship, but because of useful things, so that this workshop is these days really give you knowledge, give you something like what all of us needs, inspiration. So thank you very much. Gergely, this is your word.
Okay.
I wish you a nice.
Peter. And I hope you can stay with us at least for the beginning of the conference. So let me just jump over here, and I think we have some time to prepare for the first talk. So we are ready to fly to space. Let me start with space-ready FPGA hardware acceleration for .NET software, and this is by our partner company Haslayer and Zoltán Behotsky. And
That's right. Just
the question is how to make a quick
yeah.
change.
Please give me like 2 minutes to plug everything in. Yes.
But I think we need this to how to place this because we need this for the.
Igen, de nem fogjuk tudni közvetíteni.
Akkor bejelentkezek tudnom. Hova portál? Nyilván kisebb vagy? Ja, köszönöm. Oké. Köszönöm. Jó, ide le tudjuk rakni.
Nyújtani kell meg.
Nem, ő csak prezentál, és innen megy a hang, és akkor úgy.
Az, hogy nem fog menni.
Miért?
Mert a beszédet fogja mutatni. És
azt ki tudjuk közvetíteni.
igen? Jó.
Sorry, azt hittem, ezt ki tudják.
Akkor nem,
Kaptál egy.
nekem most jól.
Nem a YouTube, hanem a
Ja,
szerencsére van kell.
Csak pont találom a jelzőben.
So when everybody is paying attention, but nothing useful is happening, I think it's called dead air. So that's what we are demonstrating now. Just. Okay. Okay.
So,
És akkor screen share.
how is from outside?
Okay.
Akkor viszont nem tudod használni azt a nyomogatót, csak mondom.
Nem baj. Yes.
Okay.
Okay.
So
is my voice okay as
sorry,
well?
I think it's working now. So please, sorry.
All right. Yeah. So thank you everyone for your patience here. So I'm Zoltán Levosky, as we have probably also heard, and I'm from a company called Lombic Technologies. We have been here a few times. Actually, I'm very proud that I was there with my friend and business partner Benedek on the very first GPU day, 11 years ago. So that's quite a heritage. There are two colleagues of mine who worked on this project who can't be here today, David Elsai from Lombic as well, and Ernő David from Wigner. But let's see what we actually have to figure out here. Just a bit of interaction before anything else. Lombic is actually mostly a software development, a web development company. We work with open source Microsoft technologies, .NET mostly, and mostly on web projects with a content management system called Orchard. Now, Orchard is an open source software. We are also very much focused on open source. And during these endeavors, we work with companies like Microsoft itself, or Live Nation, or institutes like the Smithsonian Institution. But when we are not doing some web development, then we are doing some research and development, like on our Heslier project. But before talking about that, let's talk about you. Let's suppose that you are doing some number crunching, all right? And by number crunching, I mean some computations, some heavy computations in the field of, for example, scientific computing, of course, or something in the field of machine learning or AI, or image or video processing, which are highly parallelizable computations, or computer vision, which is tightly related, or anything with data compression. Now, if you have some computationally heavy algorithm or application here, then you probably want to make it faster. And to make it faster, you have a couple of steps, a couple of general steps to take, which is probably familiar to everyone here who has written a bit of code. First, you can profile and optimize it, so figure out what is slow and make it faster. But let's suppose that you have already done that. Secondly, you can also parallelize it to make it multi-threaded or use multiple computers even, but let's suppose that you have already done that as well. And of course, you can use faster hardware. In the cloud, you can scale up fairly quickly, or you can use more hardware, more servers. You can also scale out. Now, you have done all of that. What is it that remains? Well, everybody knows the answer because we are on GPU day. Of course, you can use some heterogeneous computing approach. So hardware accelerators like GPUs or FPGAs. Now, let's talk about that last part, FPGAs, a bit more. Probably most of you are familiar with them, but for those who aren't that much, FPGAs or field programmable gate arrays are pretty much computer chips that can behave like any other computer chip, within limitations, of course. So they can be dynamically rewired on the fly to mimic some kind of other chips to do some computations. This is cool, but why do we actually want to use FPGAs? We want to use them as compute accelerators because they have some unique benefits compared to, for example, CPUs and GPUs. And here is how they compare. This is just a totally non-scientific, very rough comparison, just to give you an idea. All of this highly depends on, of course, the specific application and the specific devices. But let's talk about the parallelism first. So how many things you can compute at the same time? With CPUs, the first chart and the bar in blue, I would say that they are on the lower end here. So in a CPU, you have something like maybe 8, 4, 8, 16, perhaps 32 cores, but that's about it. GPUs in orange, on the other hand, are on the other extreme. They're highly parallel computing devices, highly parallel architectures with thousands of little processing cores. And the FPGAs are kind of in between, although they're not cores on an FPGA, although that depends on the specific device. Now, what about the complexity of programs you can run on these? So, all right, we have parallelism, but what can we actually do with these devices? And CPUs win here because if it's software, you can run it on a CPU. GPUs are on the other end, but on the lower end, I would say here, because the programming model there is much more limited. And FPGAs are kind of in between again. All right, so still, why use FPGAs? Because of the last thing, power efficiency. And power efficiency is something that, of course, matters in mobile devices like this laptop, but also if you do a lot of computations in a data center where power consumption and subsequently air conditioning is the major cost factor in actually running a data center. Because FPGAs are very power efficient. The reason there is because when you use an FPGA, it only computes what you need to be computed. There is no operating system to run, no other software. There's not even an instruction set for a processor because everything is hardwired. Okay, that sounds great, but what's the catch? And the catch is that utilizing FPGAs is hard because it's not easy like software development, but it's hardware development. It's super low level. You have to think in terms of wires and logic gates and clock cycles. It's very hard, very slow. Even if you are experienced, it's a lengthier process than writing a program. But with Heslier, we intend to bring this down onto the software development level. Because what is it? Heslier is pretty much a tool that takes a computer program and converts it into a piece of FPGA logic. You could also say that it takes a computer program and creates an equivalent computer chip out of it. And not just any computer programs, actually. We are talking about .NET. You know, the .NET platform is an open source cross-platform programming environment. It's not a programming language. It's a platform that supports many programming languages. The most popular one is probably C#, but also C++ and functional languages like F# or scripting languages like Python. So all in all, we want to have the computing benefits of FPGAs for all of us software developers. That means that if you have a highly parallelized application, then you will get a performance increase. Secondly, you get a power efficiency increase, so you can compute more stuff with less amount of power. And certainly, it's still programming as usual. So all cool. Now let's see it in action. And I'm now switching over to Visual Studio to show you a bit of code. This is some C# code here, which is, well, a parallel algorithm. This is nothing actually useful. This is more like an exaggerated example of the kind of algorithms that are suited to be accelerated with FPGAs and thus with Hastier. This is a massively parallel algorithm, also called embarrassingly parallel. Because what it does is that here, there's a bit of logic. This just simulates that we are doing stuff. By the way, this code and all the other samples and the whole thing is up on GitHub. I will show you the link later. And this logic is executed in tasks. This code starts many tasks. You can think of tasks as kind of threads, but they are managed by the .NET framework. So there's no thread starvation, for example, but it's for multi-threading. And we start actually this many threads. This many is 280. We start 280 tasks threads here. Why 280? Because that many will fit on this device that I have here and this FPGA that I will use for the demonstration. Because these 280 tasks, when I run them on a CPU, like on the CPU of this device, they will run just on those cores that you have there. On my laptop, that would be 4 cores. On this device, it's 2 cores. But if you use Hastier to convert this into a hardware implementation, then you get actually 280 little processing cores all working in parallel. You will get a hardware level parallelization of 280. And this many will fit because, of course, FPGAs are not limitless. This many resources are there on this particular device. And pretty much that's the algorithm. It does some stuff on 280 threads / tasks, sums together the outputs, and that's it. All right, let's now actually try this out. And I forgot to copy the script. So sorry about that. But let me open a serial shell to this device here. This is an FPGA board, a development board based on the Zinc family of devices, and that means that it has an ARM CPU coupled with an FPGA, and it runs Linux. So hence why I have a shell here. And what I'm doing here now is running a demo application. It will take a bit of time. We will see the results in a minute, like literally about a minute. What happens now is that first, that parallel algorithm will be executed as software, so on the ARM CPU of this device. By the way, this is a dual-core ARM CPU clocked at around 650 megahertz. Sorry about that. And once the software execution is finished, it will execute the same thing with Hastier on the FPGA part of the Zinc 3 times. This actually happens, so let's see the results. Let me scroll up a bit here. Okay, scrolling apparently doesn't work, so like here. And here's the results. Well, here's one of the results. On the CPU, it took around 25 seconds. Okay, so for 25 seconds, these 2 cores churned away. What happened to the hardware? If you scroll down here a bit, we will see the results of the first hardware execution. And that was about 330 milliseconds altogether. So it took 330 milliseconds from the start of sending the data from the CPU to the FPGA until we got the results back. So that was the total. Actually, So it was about 100 times faster, or 2 orders of magnitude faster. Now, if we only take the hardware execution into account, actually, then it was 240 milliseconds only. So this this round trip to the FPGA takes a lot of time actually, but that diminishes if your algorithm takes a lot of time to compute. So while this was a synthetic example, I hope it provides a glimpse into what's possible with hardware acceleration. I will show you a couple of other results as well, because we have full support for the VITES framework of the FPGA manufacturer called Xilinx. But this allows us is to target multiple devices, not just these devices, but also accelerator cards in data centers. The Alvo family of Xilinx is widely available in cloud providers. Those you can use as well. And also target aerospace applications, because this device here is actually the same thing that's widely available as, as the onboard computer of new space satellites. So this little piece, actually not the whole thing, the actual device is just a little thing in the very middle. This is pretty much the same hardware that you can find on board of satellites and drones and robots. So with this, you can pretty much run exactly the same codes, both in the data center for example, image processing tasks when you process satellite imagery, and also the same code on board of a satellite to pre-process satellite imagery right there on board. A couple of results on the Alvo boards, so those FPGA boards that are available in cloud computing providers. We got speed ups somewhere from 4 times to 34 times, and the power efficiency increase was a bit better, something from 20 times to 120 times. Now the power efficiency translates not just into saved power, which is good for the environment, but also into cost savings, of course. On the Zincs, so on these smaller devices, we got actually nicer results for some reason. The baseline there was the 24 times speed increase for image processing algorithms. These are just a couple of sample algorithms that you can see on GitHub, up to 100 times, and similar things with the power efficiency increase. And one thing that might be interesting for those people working on scientific computations here is a POSIT number format, The cool thing it has here, and with high-level tools like this, is that you can even implement your own number formats. And that's what we actually did. Well, we implemented a number format invented by a mathematician called Dr. John Gustafson. We pretty much created a .NET library, and with a flip of a switch, we created the corresponding hardware implementation with Hestier, which means that we now pretty much have a POSIT processor. And why POSITs are good is because they promise to offer better accuracy and better range with the same amount of bits than the IEEE standard floating point numbers. They're useful if you do some scientific computations. Pretty much that was it from me. If you like this, and I really hope you did, then please check out the SDK. It's up on GitHub, and be ready, because hopefully I would think that definitely you'll hear more from FPGA computations in the near future. So thank you very much, and I think we have a couple of minutes for questions if there are.
Thank you very much. It's really exciting to do everything in real time here. So thank you very much. And
A lot of cables there.
Yeah, a lot of cables at least. Okay, so questions. Please do speak up because of the outside people.
You mentioned image processing. What's typical complexity of processing algorithms?
Sorry, could you speak up a bit? I have a bit of a hard time.
So
Thank you.
you mentioned image processing as a use case. So what's the typical complexity of image processing algorithm? Here is it just a kernel convolution or maybe neural network inference?
Should I repeat the question?
No, it would be very useful.
Okay, so the question was about what's the typical complexity of the image processing algorithms you can implement here. It's just some simpler image processing, or it's more complex like neural networks. The short answer is it depends. It depends on the capacity and the other capabilities of the device, what makes what's feasible. This is a relatively small device. So these data center accelerator cards I mentioned have a capacity 50 times more. On this device, I think it's useful to just do some simple kernel processing right away. One of the samples we use here is some contrast modifier logic, which is quite simple but highly parallelizable. There's no intelligence of sorts there. That being said, there are also FPGA optimized versions of machine learning libraries. We didn't do anything with that yet, but Xilinx, for example, offers some pre-baked libraries of that sort.
Further question? Matthew, please.
In the context of using FPGAs in space, which property of FPGAs is more important, the power efficiency or the reconfigurability?
So the question was, in space applications, which property of FPGAs is more important, power efficiency or reconfigurability, or perhaps performance? But I think that right now it's actually power efficiency. So we are talking about, when talking about these kinds of Zing devices, we are talking about new space satellites, which are small and nano satellites, like the small CubeSats. That means that power is the biggest constraint, both electrical power that you get to run devices and both what you can dissipate as heat. That being said, also with new space, reconfigurability and pretty much the ability to update everything on the software side on your satellite becomes more and more important. So I think that will be more important in the near future. Right now, power efficient side.
About number formats, so also sometimes people are using cover. So do you have access to type of number formats like double precision, single precision? Is this all available? This hardware?
So I didn't quite understand the first part of the question. Probably.
Precision, is it available both formats on the hardware or
So the question was whether single or double precision floating point is available. Not with Haslier. Generally, it's possible with FPGAs. I mean, in principle, it is also possible with Haslier, but it's not really efficient. Implementing any kind of floating point, also posits on FPGAs, is costly. It's also costly in CPUs. We just don't know about it. When it's about FPGA computations, we prefer not to do any floating points, just integer and especially bit computations. But you can implement it in a soft way, like with posits. That's the only way to do that on this device actually. But there are certain devices that have hard floating point cores as well, where if you use the manufacturer's libraries, you can get direct support.
Okay, time is running, so Zoli will be here for the rest of the day, I think.
Yeah, until lunch.
Until lunch.
Until the end of lunch.
So I would have a couple of interesting questions, but thank you very much again for you.
Thank you.
And, next speaker, yeah, for this
which is Zoltán Kis from the TIFÜ, and speak about how can we put like 200 plus GPUs in one HPC available soon. Let's see. Okay, thank you very much. Let me do this. I'm sorry you have to see my presentation instead of the castle here, which is much nicer, I guess. But I try to be as interesting as seeing the castle with this shiny, nice weather we have. Yes, that's fine. So myself is an IT guy, basically. So I'm talking about infrastructure. I'm not talking about the usage and the scientific stuff. I'm sorry about that, but you will hear lots of talk about science behind. I will talk about the infrastructure because we are passionate about infrastructure and also about GPUs, because for quite some time, like 10 years now, we are serving our users GPU-based HPCs. And for quite long time, we've been a provider for Hungarian community, including research and academia, providing GPU resources as well as CPU resources and coprocessors and so on. So we are the Hungarian academic and research infrastructure provider. So we are also providing like a network infrastructure for most of the universities and academia, and we are building our services upon that. So most of you probably already using our infrastructure without knowing it, because we are serving basically most of the academia with network. So if you are like seeing like EduRoam or connecting to this infrastructure, or you're using your internet in most of the schools also, that's what we are doing. So we are trying to build infrastructure services on that, and one of them is HPC. We've got history in HPC. We are doing it for 20 years now, and we're quite proud to be upgrading the infrastructure very, very soon with the latest hardware. So what I will talk about a very few words, but HPC is, and talk about the program here, and then move on for our development projects and all the details what I can share now. So just basic few words of HPC. So HPC is a central computing capacity offering for all the scientific institutions that would not have the bigger capacity they would need for their projects or their research. So that's would require generally a nation to have a central computing facility which they can use, and have the researches to be faster, to be run faster, and have the cost and time reduced, and have faster results and bigger results, and have like a real breakthrough to be achieved with bigger hardware if they need. So that's the scale of hardware is not the typical, it fits into the budget of one institution. That's the HPC. The HPC is typically very tightly coupled, a number of servers that has a very tight connection with each other, and also very obviously cutting edge hardware inside. So all the nodes and all the storage itself is connected to so very tightly coupled with each other to have this very fast processing power on one big project. So typically clusters or clouds are allowing to have a separate processing power for the servers themselves, but not scaling for many of the servers. HPC is capable of doing that. So have very special connection, tight connection. There must be obviously one data center, all the nodes and so on. So about our current facilities, we've got a huge GPU accelerated machine, but it's already 5-year-old. So it had about 240 GPUs in it, offering about 254 teraflops of computing power, which means double precision floating point computations per second. So our biggest machine is now in Budapest, and now we have Kepler GPUs, K20, K40s in it, but it's obviously becoming older and older, but still a very nice machine to try scaling and to use. It's heavily used, so you can tell it's like queuing most of the projects there. It's a continuous usage. Still, and those machines. One of our machines are shared memory, so like a mainframe, you can actually address all the memory. Applications like the gene sequencing or something like that would require a huge amount of memory to be unstable, but let's hope for the best. So what we are doing now, we've got a bigger project here, not only an infrastructure pre-development project. So what we start is basically building a whole new knowledge transfer project with the competence center. So the HPC competence center is now established in Hungary, which is also part of Euro HPC efforts. So this is a Europe-wide effort of growing competence in HPC, because it's quite special infrastructure, also quite expensive infrastructure. So you should have knowledge to use it, and a bit obviously generally a bit harder to reach, to use, and so on. So we've got the competence center, a number of staff actually working on knowledge bases, tutorials, workshops, conferences, and PR stuff and so on. So you can find us at hpc.kifu.hu. We've got also a connection for SMEs, so we are open for the smaller organizations not coming from academia, and we are building obviously the infrastructure itself. I will talk more about the infrastructure itself, but you should also visit our site for the competence part. So we've been serving community for 20 years now. There's a really nice subpage at our webpage for if you want to see what was the beginning of those really nice Sun HPCs in the past. Now we are aiming to keep Hungary in the top 500, is the world's top 500 most powerful machines list, and aiming to have a new machine that would be installed in our already existing green data center in Debrecen. It's really nice, award-winning architecture there, and we are wanting to have mostly free-cooled, warm water-cooled system with waste heat reuse. We will have about 1 megawatt of power to serve this new infrastructure there, and have most of the cooling capacity and UPS facility serving there. And this would allow us to actually reuse the waste heat also, and allow us to use specific chillers for not using these compressed machines to have a classic cooling infrastructure, but instead use only
most of the vents only for most of the day. It's free cooling. It's not just just using vents to generate airflow instead of using the machinery to produce cool water air. And also this a water spray system, which makes it cooler on the warm days. We are also working on the acoustics for the nearby facilities, not to affect those with this new machinery that will run and make noise, obviously. So we are moving out from our current facility. So all our current HPCs are now moving out, and the main GPU machines or in Budapest, so moving out from Debrecen to Budapest, but you can reach it with all those machine IPs and what you used before. And our new and the Hungarian dog breed already and coming from the area of Debrecen, and this was one of the votes that was coming from a community when we asked them what to name the new machine, and it will be a Cray. Cray is one of the most high-end HPC vendors out there with very big heritage of producing HPC hardware, and now we will have this very dense high-end machine installed, the very same one that all of the big European and US vendors will also use. This hardware is a mini exascale machine, so the very same one will be those systems that will be installed in pre-exascale in Europe. The Lumi in Finland would be one of the pre-exascale machines in Europe built within 1 year, and the new US exascale machine built within 1 year will be based on very same technology what we will using here, obviously in a smaller scale. So what's under the hood? So that's about 20,000 of CPU cores inside and more than 200 GPUs. We're already planning an upgrade here. So we are aiming to have at least 10% more of GPUs and CPUs inside. That would add up for at least 4 petaflops of GPU computing power and almost 1 petaflops of CPU computing power at the end of the upgrades. That would mean we will have GPU accelerated nodes and CPU only nodes as well. I've already talked about the shared memory system with 1 big memory to be addressed by 1 application, 1 OS with 9 terabytes of memory addressable. And we are working on AI partition with GPU nodes that would have 8 GPU within 1 node to have highly workloads. And it will have a very big super fast storage with NVMe disk and so on. So that you can find the details on our homepage. So if you're interested in, we've got the exact processor types here, the amount of RAM within the nodes, the interconnect, and we will have details on. We will also have archive system with 10 petabytes of storage. I can talk a lot about why we're choosing, but let's move to software. So there, if you can see the software here, those will be licensed available for academia. So most of the high-end HPC software will also be available. Contact us if you want any any other specific software for this already installed in HPC environment, we might want to purchase them as well. So we've got a new portal system. We're planning to have containers and Jupyter to be available in new machines, but obviously we won't have container running facilities only because we would need still, people generally need still hardware and their own way to bring their software. And we would want to support them also with the deployment, an automated deployment process. So one can actually use some kind of data provider there and build a software automatically and then do the visualization as well at the end. So we have a visualization subsystem at the end. You can actually check your data in 3D. If you want to see our publication of results with that HPC Echo on our site, check it out. For the conference of our users to actually talk about use cases of our HPC. It will most probably be virtual only, but please check if you're interested. We will have a very complex system of support. So if you don't really know what HPC is, we can have your project be run on HPC. Most probably just contact us with the different kinds of support solution. And also we are hiring if you're interested and if you want to work with HPC in the future. Thank you very much.
Thank you very much. Speak up.
So you mentioned Lumi and the US exascale computers. Are you going to have AMD GPUs as well, or NVIDIA GPUs?
No, NVIDIA only for its son. Yeah. We believe that AMD GPUs will have similar kind of performance and usability within a year or so. But currently, we can see that the ecosystem behind NVIDIA is much more advanced currently, which would make our users to easy to adapt to these GPUs. But in terms of price performance, AMD is now very comparable or even more advanced.
Further question?
I have more. Okay, go ahead.
Go ahead. Please.
Okay. So how can you say a few words on how one gets access and what is the pricing? Because in Hungary we have this közbeszerzés, and that's a pain in the
Okay, so currently the HPC is open for academia and research for free. We are now in the process of for our offering to create our offering for SMEs and our actual cost to in the future how we would offer our services for SMEs as well. But now we are launching pilots for SMEs, which would also be free at the beginning. So just contact us and we will answer you specifically for your project.
Thank you.
So, please.
You already started to answer it. My question was about what kind of SME connections do you have, or what kind of partnerships are you seeking?
All kinds of. So we are currently building up our SME ecosystem. We would want to have a separate offering, for example, the software infrastructure, the portal system, and so on for SMEs dedicated. We are seeking all kinds of collaboration. So just speak to us and we will see.
Great, thanks.
Okay, quick.
That's very big. So with regards to
engagements, is your infrastructure more prepared for dedicated hosting, or do you also have capacity?
If it will be dedicated or on demand. We are working generally on an on-demand basis. That would mean that all our users have to queue, and our scheduler will actually allocate the resources for them. So most of the users won't be able to actually use our infrastructure as they have their proposals submitted, but for some time, as after they. That's how it works now.
Okay,
Thank you very much.
so thank you very much. Is available in digital resources, and now we are returning to Mate. I think Mate should know by everyone, but he is Mate Nagyegri. He's today from Stream HPC, but earlier from the GPU laboratory, and Mate will speak about the standards in HPC. Maybe a technical information. So we have a list for those who are attending the meeting on the site. So please, during the coffee break, sign if you haven't made so.
Okay. So I would like to welcome everybody. My name is Mate Ferenc Nagyegri, and I work at Stream HPC. And first, a few words about us and who we are. We are a software services company, and we develop software solutions in HPC. It's no surprise. We tend to feel more we develop libraries from ground up, but also port existing solutions, and we also tune performance to various architectures. May that be either some commercially available, but we also do projects with custom SoCs and custom hardware to develop software solutions for those. And in the talk, there will be some of the projects which we were involved in recent times. Let's try this one. Okay, then. Speak just a few words about graphics and interconnect technologies, because that is one place where standards rule supreme, or they are widely adopted. And then about the available compute APIs that are in use today and are popular, and some recent changes and advancements in the landscape. So why talk about internode communication? So if one wants to increase the compute capabilities beyond what is available in one single node running one operating system, then some kind of network communication has to be involved. And if one looks at the scientific framework, the dominant standard, which is used to define network communication across nodes. And while there are a few contenders, for example, HPX and Zero Message Queue, which they are more novel solutions, so they are a lot younger, but they do implement their own network communication semantics. And of course, the network stack has various layers, so software, protocol, and physical implementations. But as programmers, we are primarily concerned at the topmost interface which we deal with, which is the software layer, and there MPI is by far the most adopted. And while NUMA architectures exist, which and NUMA covers a lot of ground and does a lot of the so in by NUMA here I mean architectures where one single operating system could address the entire memory of the entire system. And while these architectures exist, naturally there is a limit to their scale, and in the chase to exaflops, NUMA architectures usually don't scale to those sizes. And for a very long time, I'm sure that everybody who is into HPC knows Mellanox and the InfiniBand brand of connections, which are very popular, primarily because of the sheer bandwidth that they can provide. The easy adoptability, it's just a PCI Express card, or sometimes it's even integrated to the motherboard, and the extremely low latency by which InfiniBand endpoints can communicate with each other. And since NVIDIA acquired Mellanox, but also because reach the operating system and the network I/O stack, a lot of other competing technologies and standards have emerged. For example, CXS, CCIX, OpenC API, which are open standards to implement the physical layer of the interconnect, and then the vendor solutions, they are essentially implementations of those standards. But still, the takeaway message is that even though there are various physical implementations and various network protocols which sit on top of it, not just TCP, which is known from Ethernet, but these technologies can use other network protocols as well. As end users, we are mostly dealing with one communication API, which is MPI. And in the graphics industry, a similar is in a similar position, in the sense there were a handful of graphics APIs being used, but dominantly there was one proprietary solution from 3DFX, which was the Glide API, and some of the games there even had a Glide backend, and then proprietary and cross-vendor and cross-platform, either platform solutions, which was DirectX, that was specific to a platform but cross-vendor in nature. OpenGL was cross-vendor and cross-platform. So these technologies competed with each other. And if we fast forward to today, but we don't have to fast forward actually today because it's been like this for a very long time, we have a handful of platform solutions, if we look at Metal, for instance, or DirectX, but they are always cross-vendor in the sense that they support all the vendors which are available on that platform. And then there are the cross-platform and cross-vendor solutions. And proprietary APIs essentially don't exist anymore. There was one very short-lived AMD's Mantle API, but that lived only for 1 year, I believe, or 2 years before it became discontinued. So in both the network side of things and in graphics technologies, standards do exist, and they reign supreme. there are no proprietary solutions available, which us as developers would have to deal with to some extent. And the message is that even though that these standards exist, the existence and the proliferation of standards do not conflict with either competition or innovation. So if somebody would say that there is no innovation in the graphics industry, well, that is not that's a statement that isn't true. If we look at just the going by the images alone and the quality and new techniques of developed in the graphics industry, but more on the existence of standards and APIs in the graphics space a bit later. Now for compute APIs, the situation is slightly different. And if I would say that that the term GPGPU to some extent has became a synonym of CUDA acceleration, and this is just one pet peeve. But if somebody says that we support GPGPU, and that means that we support CUDA. If you look at the asterisk or you open up the article, it means that there's CUDA support in the library which we are talking about, or the technology platform we're talking about. So there is a persistent CUDA hegemony, which isn't by chance, and I will talk about that just on the next slide. So there is a great deal of both market and mind share in how CUDA is the go-to technology when using when wanting for those for that being the default. Like NVIDIA has been a constant pioneer in the domain of GPGPU algorithms, and they aren't the sole pioneers and investors, but by large, with the largest investment. So if NVIDIA has developers in just about every single domain framework there is, even if it's for developers of libraries to integrate CUDA acceleration. The CUDA ecosystem has gained a reputation for its stability and maturity in its 15 years of existence. And there is also a wide assortment of performance, turnkey-ready domain libraries that has won the hearts of many scientists. So it does lower the cost of implementing whatever framework we're talking about, not having to deal with the domain libraries because they are readily available. It is a comfortable programming model, and popular comfortability comes with popularity as well. So it's one after the other, or the chicken and egg, which now exists. And there are partnership programs which provide upfront benefits to those who join them. So this is why CUDA is in the place it is today, even though it is a proprietary solution. So one can only use it on one vendor's hardware. Even though we saw that portability and being able to go between vendors is a key property in other places. So why not compute? Penetrating the market to the same extent as CUDA has. OpenCL is one of the most persistent contenders in this space. And in the domain of GPGPU itself, it has not reached that penetration, which was or has been expected of it. But nonetheless, it is a extremely popular programming model. Partly because of its simple ABI, so it is a C library itself. So it's a runtime library, which if one can talk to C, then one can talk to OpenCL, which is just about any language, any framework, anything, anyone out there. And it has seen popularity not just in the context of HPC, but also custom embedded SoCs, as I mentioned, AI accelerators, digital signal processors, and there are a lot of OpenCL implementations out there which aren't public or people don't know about it. So if some company makes an accelerator of their own custom SoC, then they will most likely put OpenCL as a programming model simply because it's well known. So they can recruit developers to code for it, and it's easy to implement. So it has seen popularity, mostly, or its popularity is greater outside the GPU. And another contender which primarily HIP, which is AMD's answer to CUDA. And without quoting the HIP quoting guide, just the important part. So HIP is aimed to be C++ runtime API to develop applications for both AMD and NVIDIA. And you can write code with very minimal changes if you have an existing CUDA implementation. And that is because syntax-wise, they are very similar to such extent that they are mostly source compatible. So it's just changing the names of a few symbols and identifiers, even with macros, for instance. And a CUDA implementation is a functioning HIP implementations for most intents and purposes. And the domain libraries are also readily available. Moreover, they are open source. So although this correlation is not causation, and that is an extremely important statement here. If somebody would look at the market capitalization, the stock prices of AMD, in 2016, they launched their GPU Open initiative, which means that they open sourced essentially their entire software stack. So starting with the HIP compiler itself, but also the runtimes, the drivers, and everything. It's completely open source up on GitHub. Anyone can compile the driver, the kernel, the runtime, and everything from themselves and run it. So, and because of this, this is one of the aspects, and this curve is true actually for most big tech companies lately. But one of the reasons why the aforementioned supercomputer in the United States, the Frontier machine, will be using AMD GPUs is because it gives great power to the system administrators and the users of both the users and the system administrators, that they see everything and they have control over the way they like. So in some sense, one could say that HIP is the open source version of CUDA. And yes. But us as end users, we said that when we are developing graphics or thinking in terms of network, we have one API, we implement it, and we're done. We implement our application against one API, and we're done. But what do we do if we have just these two technologies and they are very close? So as I said, that they are almost source compatible, but they're not fully source compatible. So just two vendors, just thinking of two vendors now, we want to target AMD NVIDIA GPUs and CPU architectures. Then how many backends does my application need to have? Well, and in those cases, and everything that the domain libraries, the BLAST library will just invoke cuBLAS and QFFT and the NVIDIA libraries. So if HIP is designed in a way that when run on NVIDIA hardware, HIP completely evaporates and isn't even linked to, and it's not used. As far as I know, it isn't even linked to. But it mostly evaporates. But projects usually don't go this direction. If they support CUDA, then they have native CUDA support as well. So CUDA and HIP, however similar, these are two code paths to take into account with two build definitions as well. Now, if somebody does target HIP and they have a working HIP port of an application, then HIP CPU is another backend which is worthwhile exploiting. HIP CPU is a purely C++ 17 and OpenMP implementation of the HIP programming model and transitively maps cleanly to CUDA. So if anybody has ever wondered that I have a CUDA application and I wanted to debug it or parallel on the CPU, then HIP CPU is a very good way to achieve that. It's just including a different library. Moreover, it's a header-only implementation of CUDA, and any C++ 17 compiler can compile it. And then just attach an ordinary debugger to it and debug the kernel, stepping through breakpoints, anything that your CPU debugger supports works. And potentially one wants to have a vanilla standard implementation without any of the GPU technologies. So that's 3 or 4 implementations, which are just AMD GPUs, NVIDIA GPUs, and CPU implementation. That's a lot of work. 3 build definitions, 3 code paths to maintain and test for. It's a lot of work. And we haven't even accounted for Intel hardware, Intel integrated graphics, and the soon to come dedicated GPUs. It's not soon to come, they already exist, the GPU. So one starts to question, isn't there a better way? And if one wants to minimize the work and the effort, then yes, OpenCL did this 10 years ago. We had one code to target CPU, GPU, multi-vendor, cross-platform, everything. So we did have solutions for this a decade ago. And what has changed since that makes me say that standards will have a greater role, or will likely play a greater role in the context of GPU and HPC as well than they do today. Yes, well, if I would have to say what's the point of standards, then somebody just looks at this image and yes, what is the point of standards? It's ultimately less suffering for end users, less things to worry about, less things to care about, and there is no great difference in the feature set on what's on the right. They essentially do the same. So standards are a good thing. And now I'm using the newer level of OpenCL consciously. So what has happened in recent times? OpenCL 3.0 was released recently. It is if somebody hasn't heard, it is a reimagination of the API. And what it did is that it builds on top of the widely adopted 1.2 version. So so much so that OpenCL 3.0 and OpenCL 1.2 are source compatible with each other. So no code change whatsoever is required. And OpenCL 3.0 adopts the Vulkan-like have a slim core, which is a very minimal subset of the API and language, and everything else is extensions. And Vulkan has gained insane popularity due to this approach. And OpenCL has gained a great deal of momentum from this decision. So even though OpenCL 3.0 is fairly new, I think it's not even half a year old, or roughly around a year old, and there are readily available implementations from Intel, ARM, Qualcomm, and even NVIDIA. If somebody updated their NVIDIA runtimes in the last month, then they have a 3.0 runtime on their system. So vendors are behind this idea, and since the last year, a little short of a dozen extensions have been already published to 3.0. Starting with the subgroup support, and there are AI extensions for machine learning operations, 8-bit operations. There is, if somebody looks at the Kronos blog which has recently shipped, then there are a lot more extensions to talk about. Specifically, there is even Vulkan as well, which is a preliminary extension. So OpenCL3 is, it lowers the bar of adoption, and that is what was the biggest problem with OpenCL, that 2.0 and versions onward started mandating features which always, there was some feature which was hard to implement for a vendor. So a lot of obligatory features got in, and that's why nobody really wanted to implement it, because there was always one thing which they couldn't do, or if they implemented it, would have performed poorly on their hardware, and that's bad press. So instead, slim core API and everything else is extensions. Ecosystem. So the ICD loader, which loads the implementations, the vendor implementation, big OpenCL, has gained a new capability to define layers. And now one doesn't have to use library intercept layers and things like that. It's a standard mechanism to load layers, which can add missing features to a runtime. So if somebody's implementation is missing a feature, then it's easy to add a missing feature to an existing vendor implementation, validate the correctness of the user application, trace the application, profile the applications. There are many. It is again something which the Vulkan API has done and is very popular to use various layers, which can be turned on and off at will. The OpenCL SDK serves as is intended to serve as a one-stop shop for developers. So if somebody goes onto GitHub, it's in the Kronos user, under the Kronos user, there's an OpenCL SDK, which you can clone, and then you get a complete development package. And the initial set of native samples using C and C++ has been awarded to Stream. So it's coming to GitHub near you, and it's likely next week that all the samples will ship. And we applied for this project because we think that high quality SDK to samples and teaching material is very important to the ecosystem as a whole. And we wanted to lend our expertise to the Kronos group to develop the initial set of libraries, and then the initial set of samples, and then more samples to come. And the 3.0 also defines the semantics of how to have layered implementations. So an OpenCL runtime running atop another API. And most notably, the first such implementation is from Microsoft. It's OpenCL on 12. So it's an OpenCL runtime that is running on DirectX 12. So it can be considered as the baseline of OpenCL support on the Windows platform, because if every GPU vendor has to have a DirectX 12 runtime, and as such, they have some baseline which OpenCL cannot go under on Windows. And this implementation is supposed to work in the WSL subsystem, so even in the Linux subsystem, OpenCL and OpenGL acceleration is available. And there are quite a few graphics and compute standards, and each can be layered on top of the other. So this is a bi-directional or a matrix of mappings, and it does to some extent introduce the M times N problem. So vendors are still encouraged to implement the APIs and have first-party support for it, but layered implementations is very useful to provide baseline of support for all of these technologies, and also to fill in the gaps of platform support or vendor support if there is a gap in some place. And in this diagram, SQL implementations aren't noted, but what are SQL implementations? SQL is another Chronos standard, I would say slightly less known than OpenCL, but that will change fairly soon. The SQL 2020 has been recently released. It is the newest version of this standard. What is it? It's a single source programming model similar to CUDA or HIP. So you write, it's a C++ API. So it's you write one source code which has both the host side and device side code in it, and you compile it, and it will run on a wide variety of hardware. And this is the current set of known and public SQL implementations. The top one, DPC++, is Intel's implementation, and it supports everything which all kinds of Intel hardware, CPU, FPGAs as well. So here, because Intel is invested in both FPGAs, graphics, CPU, and they have this one API initiative, which translates to write one code and run it on a wide assortment of hardwares. And the power of their implementation is that it's also open source. It's up on GitHub, and because there is a great momentum behind SQL, CUDA support has also been added to the DPC++ implementation of the Intel LLVM implementation. It can run on NVIDIA hardware as well. And there is a HipSQL implementation, which by its name would mean that it's then it has gained CUDA backend as well. It has a mature CUDA backend, RACM backend, OpenMP for CPU, and it even has an experimental backend for level 0, so it can drive anything which is Intel hardware as well. And it can do so from a single binary, which is again very important that I compile my application once. I don't have to compile it again for other architectures. And TriSQL, NeoSQL are NeoSQL I know slightly less about. TriSQL is the implementation of Xilinx, so it's an implementation targeting FPGAs. And Compute CPP is the only conforming implementation which conforms to the previous standard, SQL 1.2.1, which runs on top of anything which is supported by OpenCL and knows Spear or SpearV, so they can ingest intermediate languages. And the new standard is behind SQL, and it's increasing in popularity quickly. And how so? Just recently, GROMACS has released their newest version, which officially deprecates their OpenCL backend, and they are looking to replace it with a SQL backend. As we've seen that SQL supports just about the same number of hardware, which and the kinds of hardware as well, not by chance, which OpenCL did. And one could say, like, what does one read from this information pair? One could say that it's a loss for OpenCL, win for SQL. But I would argue that the read for is that the the Chronos standards for compute have reached a state where actually projects can choose the technology which makes the most sense to them. So SYCL, by its nature and by its compilation model and everything, is more similar to CUDA. So if a project has a mature CUDA implementation and extensive CUDA support, then going to SYCL makes more sense and is less of a work for that project. While there are other projects which don't want to deal with the C++ ABI and a C ABI, and just that it's a C runtime layer and not a language, but it's just a runtime, makes more sense to them. So if .NET, they do it via the C ABI, and they will not be compiling C++ source files because it's much simpler. So because there is no one size fits all, there are actually standards and technologies to choose from, and that is a big statement. And so there are places where OpenCL SYCL cannot or can't, and there are places where SYCL will go, where OpenCL could, but SYCL is a better fit. And again, these two standards aren't even competing with each other, but they support each other. And only require OpenCL runtimes. So the code is formulated in SYCL terms, but then anything which runs OpenCL executes it. And because there is interop between, one can invoke something written in SYCL from an OpenCL application and vice versa. So in SYCL applications can invoke existing OpenCL libraries. So how can one catalyze the adoption of both of the technologies, not just one or the other? Having a breadth or widely available open source algorithm and domain libraries is important. And for one such library, for example, is AMD's RockPrim, which the development of RockPrim is spearheaded by Stream HPC, as is RockTrust and HipCub. They are the hip ports of the RockTrust and HipCub. They are the hip ports of these two libraries, Trust and Cub. But the implementation of both of them is wired into RockPrim, so there is only one algorithm library in the RockM ecosystem, and RockTrust and HipCub, they are thin wrapper APIs around them. And if somebody wants to look at how these libraries are tuned for one architecture, well, not just two architecture, but the GCN and the RDMA derivatives, how to implement high-performing parameterized implementations of scans, reductions, and whatnot, then they can look into it because it's all open source and even contribute. Domain libraries, BKFFT, which by its name means that it's a Vulkan FFT, but actually it has CUDA and OpenCL backends as well, and it's extremely performant, and it even beats the vendor solutions, both QFFT and BotFFT in many cases. Intel's 1MKL is an assortment of libraries, domain libraries, and all of them are open source and formulated as SYCL libraries. Most of them are implemented in SYCL. And the existing CL-MAT libraries, so the CL-BLAS, CLFFT, which were developed by AMD and have been in maintenance mode for the past 5, 6 years. They are still extremely performant to such extent that that CLFFT on AMD hardware still outperforms RockFFT. When CLFFT was written, these cards were nowhere near, so they are not tuned for this hardware, but still the performance is comparable. And porting of the domain frameworks, which is the larger chunk of work, and And Stream has taken its share in that and has taken part in both porting and tuning Romax, LambD, EmberMD to HIP, and also OpenMM. So, so there's and there's already a lot available to use in importing these applications. And choice is key. So I'm not saying that only standards should exist, because vendors do need their playground when they can tune the last bolts and knobs of their hardware. So, but in an ideal world, these technologies coexist and both are supported. So the vendor solutions and the standard solutions. So some project cannot afford to have 3, 4, 5, 6 backends to target all hardware, and they can choose a reliable standard solution. And thank you for your attention. And if you're interested in joining the development of these libraries and want to work with Stream, then you're hired.
Thank you very much, Matej. Reached the coffee break, but it's time for a couple of quick questions, and you can also ask me.
So, are there any plans to expand this ecosystem into web as well? Because I seem to remember that many years ago there were some attempts with FCL, and also I see some standardization attempts with compute as well. So, how
I missed the most important word. Extend it to what?
web, HTML5.
To the web. Yes. Aim at bringing Vulkan level of support to browsers, or the Vulkan feature set to browsers. But as far as I know, the API is slightly different, but one can read up on it, the exact details. The primary concern with the because web tech or graphics technologies are a lot more restrictive on what you can access, primarily by not having pointer support whatsoever. As soon as you introduce pointers and you can do pointer arithmetic, that's a big attack vector. And that's what browser vendors weren't really happy about just when they implemented OpenGL ES back in the day, like the WebGL. And they said, okay, now we want to do this with pointers enabled. And then the browser vendor said, yes, we don't need to do that. So I would not expect to have compute grade support in browsers, but anything which can be compiled and translated to compute shaders can work. And in fact, the big feat of OpenCL on 12 is they do this. So OpenCL on 12 compiles code with pointers, C++ code, mind you. And they can transform it in such a way that it's a version of DXIL, which is without pointers, and DirectX 12 can execute it. But there is a lot of footwork in the compiler to erase all pointers.
Okay, so I think let's get a coffee, and maybe you can find Matej during the coffee break. So let's thank Matej again. Let's fly together and continue the program.
Ezt a nézetet átállítani,
hogy lassan jön So the next speaker is a very interesting talk and applied technology, and David Legradi from Technical University of Budapest will speak about the Guardian code for high fidelity nuclear reactor calculation. So we can see that how the nuclear reactor can be simulated on GPUs. Please, David.
Thank you very much for the introduction. I hope I can be heard. I'm a lecturer at the university, so I can read the faces of my audience. So if I see someone sleeping, that usually means that I don't talk too fast. If someone has contracting eyebrows, it means I didn't explain anything nice. And because I give so many lectures, I'm actually bored with giving lectures. So I'm really happy if someone is having a question in between or saying, hey, come on, you can do it smarter. I don't know whether the chairman agrees, but yeah, I'd be happy if oh yeah, and someone has it genetically. We'll see. Okay, my internet connection is unstable. Well, and it's not Miro guy, what we're talking. I'm David Legradi. That's another name, also a useful name. I'm not a GPU expert. I'm a physicist. Moreover, I cannot actually really program GPUs. If someone is doing the framework, putting there the code, I can put in the algorithms. It's more a colleague of mine who can do the programming. So I'm a physicist and I work with algorithms, and my basic field is Monte Carlo techniques. And a couple of years back, almost half a decade, we started working with GPUs and trying to do Monte Carlo simulations on GPUs. We basically had two, it should go on, okay. We basically had okay.
Opposite direction. Yeah.
But I would want to move forward. Okay, excellent. Okay, so we started up at the beginning in the tomographic image reconstruction field. My other field is medical imaging. And we wrote an image reconstruction code that reconstructs the 3D distribution of whatever data from the measured values for positron emission tomography. And currently we are writing something for computerized tomography. But we also moved to my previous field, that is not nuclear reactors. And out of all these, I consider the nuclear reactor part the flagship research. So there's a small group, a couple of seniors, one PhD student already finished, other PhD students in the mill, a couple of MSc students writing this code. And we got some funding from Hungarian national funds and also EU funds, and also from the Hungarian Atomic Energy Agency, and that provided the money for all this work. So this is the reactor. That's where we work. At the beginning, should we have a pointer? Okay, so when they were building the reactor, this is when it's ready, that's inside, and then inside the core. The blue thing is the Cherenkov radiation that you can see, and you will see the modeling of this reactor. Okay, at the beginning, in the 5 minutes, I want to talk about all the important things, and later on, I want to go into details, hoping to give you inspiration or get inspiration from your comments. So this is an ultimate fidelity Monte Carlo simulation for nuclear. Sounding term, and it's only this conference coming up next May that they have started using this word, ultimate fidelity. That is basically meaning that in reactor physics, we are getting to the point when we have enough calculation power to calculate all the neutronic processes as they happen in nature. Now, I will talk about that it's not really true, but the end result is very similar to what's happening in nature. It's not only us who is doing these dynamic calculations by direct Monte Carlo, but we only have 2 other competitors in the world who are venturing in that field. One is from CEA France, and the other is from Finland, from VTT, and they are both working with CPUs, and it's only us working with GPUs. So currently, our competitive advantage is that the GPUs are faster for this task, it seems. We could upscale to power plants. All the other competitors, they could work with very small reactors or just reactor computational models. So far, we've been the one, as far as publications and private communication went, could upscale to a power plant scale, and I will show some results for the PACH nuclear power plant, the Block 4 measurements compared to simulations. So we've been so far the first one who we only have very weak cards. Our training reactor has its 50th birthday this year, and our cards have their 5th birthday. And because of Hungarian procurement laws, very hard to get for us some new cards. So we are still working on NVIDIA 1080s. We have now temporary access to 3090, and we also have access to the Wigner cluster. And we are really grateful for that, because otherwise we could not really go on. What we are hoping for is to get access to something like the Tesla A100s, 8 of them, for example. But we could repeat the calculations many, many times, so we could see whether we are in statistical variance. Okay, so that's basically what I'm going to talk about. The rest are the details. Okay, so why Monte Carlo for reactors and neutrons? If you compare it to visual rendering, at least to my understanding, you would go with visual rendering, very basic picture that I'm talking about, that we have independent particles like photons traveling apart. They are traveling in along a straight line between bouncing surfaces. So within until the surface is just a straight line. We have very simple scatter laws. So it either is just a mirroring effect, or it goes through with a simple law. Maybe you have some dispersion of color, and sometimes you can go through like occluders or like diffusion type clouds and so on. That is similar to our application. We also published in that field because of the similarity. You only have a few material parameters, so you want to have the reflectance, transmittance, and so on, and basically that's it. For accuracy requirement, it's enough that it looks realistic, right? And mainly surfaces are usually represented by triangles, and you try to find intersection of a line with a triangle and you want to find the proper triangle. So we would need for a single photon traveling only a few registers, simple precision arithmetics, and RTX is working very good as far as I know. I don't know, no experience with that. That's why they develop GPUs to support such computation, I hope. And particles, not photons, neutrons. You have free path neutrons traveling in vacuum in a straight line. Also in a material, they're traveling in a straight line. But change of course happens according to an exponential law rather than at surfaces bounding. In total, 70 different types. Some of them are sampled with rejection sampling, not really ideal for GPUs. We always have interaction within a material. So it's always like diffusion type transport, what we have in neutrons. With gamma photons, not really. But with neutrons, you have 20 to 30 interaction before a neutron dies. That's a lot. For accuracy requirement, 10 PCM, that is percent mil, so 1,000.
You follow the secondaries after the neutron?
We follow the secondary neutrons, but we do not produce secondary whatever photons, alpha particles, and so on. Yes. Not infinite. We have in our simulations only 1 million, and it's a 5 orders of magnitudes higher that in a real reactor you can get with neutrons. So we have to be smart. We have to get the simulations working so well that it simulates the expected value, what normally 10 to the 5 power more neutrons would do. So we have really a small fraction of the real neutrons simulated. So for accuracy, even though then only 1 million neutrons, you need an accuracy that is down to 10% mils. And for geometry, you have like special materials like cadmium that even a small foil will change the whole reactor's power. So I just put down a realistic number that we use. So 15 micrometers of a cadmium foil was entered in a huge reactor model, and the power dropped by 20%. So you really have to be accurate. You cannot relax your calculation accuracy, or you have to really pay attention where you relax this calculation accuracy. For hardware, we would need large amount of registers. That's our experience. So sometimes we just can't use all the threads because we are eating up the memory. We need double precision arithmetics. So we would need, and we are using surfaces bounded or regions bounded by second, third order. Nowadays. So now I'm going into details, and I'll skip some parts if I see too many people joining under the mask. But about fission, everyone knows about nuclear fission. Neutrons causes a fission, some neutrons come free, and at the end, a new fission emerges. And if in average, one neutron produces one neutron, then you are fine. That is chain reaction. It's okay, right? But for this simplistic picture, you will not be able to control a reactor. If you just make an error of 0.1%, each generation lasts about 1 millisecond. So in 1 second, you get 1,000 generations. So in 1 second, if you just make this very small error, you will get a power increase of 2.7. And it's just impossible to control such a reactor. So you have 700% mil of the population that's called delayed neutrons that come free later from some activated nuclei. And if that were not there, we would not be able to control the reactors. Now, try to imagine the level of accuracy that you have to be handling to have a simulation of a controllable reactors for seconds. And the accuracy that you have to model your reactor to make it stable. In a normal power plant, your reactor power is growing, decreasing, whatever. You turn a node, you adjust the absorber positions and so on, and you level out the criticality. So criticality means how stable the reactor power is. But in our simulations, we can't do that. We have to get a very perfect model that is really critical on a scale of seconds. When you make this small error, and then immediately you get a huge power increase in seconds. That is not physical because it's not happening in a real reactor they would control it. So we'll have a time-dependent system now. We want to model how in a reactor, if something happens, mostly we are oriented towards accidents. So we want to avoid accidents. It's for safety calculations. We'll have a time-dependent system. We want to look what happens if there is a major failure of whatever system. And for that, we need now immense precision. How else can you solve these equations that control a reactor? Those are the equations just for the neutronics. What you have to look at is that you have differential operators, and here you have an integral operator. So it's an integral differential equation in 6 independent phase space dimensions plus time, and all these material property holding numbers, the sigmas. Those are the cross sections, interaction probabilities of neutrons with matter. They are also temperature dependent now because a reactor with higher power will heat up. And this temperature will change the neutronic properties of these numbers. So you have to add another phase space dimension, and you have to couple another full physics with thermohydraulics. And that would make an ultimate fidelity calculation. So the complexity you see, now I want to show you how it can be tamed. Weirdly enough, if you discretize those equations and you go down to only 2 energy groups, so I will show how vast this energy range is. If you go down to 2 energy groups and you do this properly, and you estimate them properly to an average value, you actually can. So weirdly enough, you can tame these, but you really need very nice tricks. And what we are trying to work for now, don't use tricks, because you never know whether your trick will fail in an accident scenario. So on the left-hand side, we have our training reactor model in our Monte Carlo code. And here, when you have some finite differences, And you see, here you see all the fuel pins. The colored ones are all the fuel pins. They have different colors because they have different burn-up. Burn-up means neutrons burn some of the fuel. You get other isotopes there, other materials. So all the colors mean different materials. You see all the pins, all the tunnels. Well, if you have finite difference model or similar, you will have such a crude model. Still, they work for dynamics very well. Sometimes they miss the exact value when criticality occurs. They get a number and say, okay, you have to divide this whatever. But differential quantities work well. When there is a change, time-dependent change in the reactor, the size of the change can be estimated, but with such crude models, very, very accurately. Of these boundary surfaces, or you can use the Woodcock technique that we use, because the temperature changes. And if the temperature changes within a homogeneous material, it's not longer homogeneous. So you have to upgrade your previous Monte Carlo techniques and use now, we call it the Woodcock method for tracking. So it's not the standard one. For something about this material cross sections, sigma, if you take the inverse of it, then you get the mean pre-pass. That's how you imagine the meaning of this number if someone is not from the reactor field. Okay, so what we can do, we can have second order bounding surfaces. You can put them for bounding cells. Those you can put it in lattices. You can make small universes filled in the lattices, so you can make very complex things with our code. Other codes can do that in the world. Many Monte Carlo codes for neutronics, but not for reactor dynamics. So this one has been established. We have to just copy the logic, basically, and that's what we did. And that's how such an input looks like, it's an X7 format. Okay, a bit more about the physics of these reactors. This is the cross section, the sigma I've been talking about. Here is the energy, sorry for the Hungarian labels, in MeVs. This is the cross section change of the uranium. You see, here is a logarithmic scale. So orders of magnitudes of change with energy, orders of magnitudes of change. And the hard part is that neutrons are born around this energy. They have to slow down to this energy before they can cause a new fission. That will get a neutron through with all these cross sections in energy varying so heavily, orders of magnitude, and do that properly. And therefore you have to represent such materials with accuracy. You see these resonances. They have to get a very detailed energy grid. So loads of data fed into the computer. Okay, more things that make the simulation hard. 1 neutron in a fission causes an average 2.5 neutrons. So imagine you start 1 million neutrons in your GPU, each thread. You will get loads of, and on total, 1 neutron produces 1 neutron. Mathematics says that 60% of your original neutrons will die, your original samples. But the rest will produce, on average, 2.5 offsprings that would create new threads, or you have to store them in registers or global memory or whatever. You have to make memory transfer. After the third generation, 9% of your original sample dies, and only 10% remains with loads of offsprings. It's not really a GPU type logic. At the end of the 100th generation, only 5% of the original state. So few samples produce loads of data that you have to store and work on. So we have to change that. So what we did, we do not kill of the particle. If there's a fission, the weight becomes 2.5 times more. That would create from 1 million static particle, 1 million particle at the end, but with weight distribution very, very haphazard. So what we did, we changed the calculation flow, like fission occurs more often, but then the weight change is less than 2.5. You can do this with expected value unbiased. You can use only non-analog techniques that is mimicking nature statistically equivalent sense. So you can make these statistical equivalences and make a lot more efficient calculations. Those are called variance reduction. That is actually my field. We also have population combing in very small time steps. We take all the population, neutron population, what we have, and they are all combed to have the same weight all around the system by throwing out particles with very small weight, splitting up particles that are high weight. You can also do that weighted by the so-called adjoint. This is the phi plus function. That is the importance of a particle. It's, if I have a particle with high weight, maybe it's in a location that is not important for the reactor, so you can weight it, and so on and so on. So you can apply all these tricks. And if you don't apply these tricks, you get these blue stars. This is the reactor power falling down. But this one is not the physics. The physics would be the red one with all the non-analog techniques. It's a slowly decreasing, exponentially decreasing power curve. But here the population collapses. So you need all these non-analog techniques to get the population stable and running. Okay. Second scale, but on the second scale, so you have a very large difference between the time scales. So you have to store them. Now, for the delayed neutrons, you have, after 1,000 generations, almost 100% of the neutrons become precursors. Precursors mean the activated nuclei that will produce neutrons later. And that means that in a real reactor, you have vast and a lot smaller amount of neutrons flying around. And just remember that our real simulated neutrons are 5 orders of magnitude less than the flying ones. So imagine that the precursors, how would be able to store so many? Again, on analog techniques, we devised a very complicated scheme to handle that. As I'm running out of time, I'll skip the most boring part, the verification. We compared it to many codes, 440,000 these functions, time and energy dependent spectra, not interesting. We also tried to do simulations using our own reactor model, the training reactor model, whether we could simulate very high power ups and power downs, orders of magnitude. And again, whether we could simulate for 1 second a stable power, and we could do that. So we became happy and started a shot in the reactor. This is the pipe. It's a pneumatic rabbit system. You shoot in the sample here, bends, goes down to the reactor core, and then we check what happens, and then we suck it out later on. And then we could simulate this transient, whether we can reproduce or not, and happily we could. That is again the reactor model. Green is the measurement, red is our simulation, and it works quite well without having to tune any parameters. So it's just a very faithful modeling. This is the joint map we generated, so the importance map. Again, I will skip it. That we did some extra population control stuff and tricks. And this one is for the power plant simulation. The power plant fuel assembly looks like that. These are all fuel pins. They are all different fuel pins. Blue one, for example, is gadolinium. It's a burnable poison of the reactor. Whatever, quite complicated. 129 assemblies, fuel pins in such an assembly. If it gets used, it will burn out. So you need different materials in all these pins in your model. Now take one of these assemblies, and each of these hexagons is contains all these 129 pins. So that is the level of detail you have to simulate. So at the end, we got so many cells, so many surfaces, lattices, universes, and so many materials, 187 isotopes to be realistic. That, I think, is a lot. So just how the modeling works, this is one assembly with all the fuel pins. The coloring is now the power distribution. In the middle, you have more power. At the edges, you have less power. When you put that together into a full core calculation, then you see how you can see through this thing because you see the individual pins. We have 44,000 pins now in this model. So if we go on, oh, that is the The same thing but static, so you don't have to be mesmerized by the moving image. This is the simulation, how well it worked. So the measurement is the blue one, and the yellow one is our simulation. The green one, the red one, is a simulation that the power plant people did with their tuned codes, specially designed for this purpose. So even for a huge power plant, we could make simulations that did reproduce the measurement. That is a so-called rod drop measurement when the control rods fall into the reactor, except for one. They simulate what happens if one rod fails to fall in. Would the reactor still shut down in time? And they do that before each campaign. It's a part of the safety procedure. We have the yellow Guardian data only to this point because it's still running. So it takes 8 days for a 1 reactor second in our card. We could optimize it a lot, but we would definitely need better cards. And this one is my last image. It's just a simulation how the control rods falling in the reactor. I will show it in a couple of more times. So you see, so you see some of the rods falling except for one. And then you see how the power decreases down in the poor reactor now. Okay, so it's out of time. That was it. Open for questions. Thank you for your attention.
Thank you very much, David. I really like the nice was a very complex. Actually, you answered my question. So what was the? So I wanted to ask how long the time does it take?
I can give some more answer to that. Now we have this 3090 card. It takes 8 days per second. But if you simplify our geometry, now we took a very detailed geometry and it's not optimized for our run. It can go down an order of magnitude, almost. So for an optimized input, we calculated this for a contract with for the Hungarian National Atomic Agency, so it has to be ready until next Monday. So, so we haven't tried a more optimized version.
Okay. Therefore, it would be a question. Yes.
So in terms of accuracy, you mentioned that your model is very, very sensitive to slight errors in distance or size. It's one thing that you can put this in a simulator, but when you do an experiment, how accurate is your measurement of how thick that cadmium foil was?
That's not your question is very valid. Not the cadmium foil is a problem, but if you build a reactor when you have 44,000 pins, can you be sure that each is manufactured to the precision that is needed for the modeling? With our training reactor, it was really a problem. We had to reverse engineer some of the details because the exact thickness of the cadmium cover of the control rods were not known precisely enough. So we had to reverse engineer some of the parts to get the initial stable calculation. So indeed, that is a huge problem to get the initial states ready to such precision that in a couple of seconds, until this transient lasts, you will not get error from the problem. We could model the power plant and it worked. So it means that for a well-defined system with quality control of all the fuel pins, whatever, it can work. So it's realistic.
I have one question. You mentioned that as the neutrons start losing energy, you associate more weight to it, so that through sorting they get sorted out as economic important, either because they lost energy or they are in a position that's not interesting. How much would the simulation change, or roughly what percentage of the simulation time goes to simulating these non-important low-weight particles? How much would it solve if you could actually take these particles out in an efficient manner?
It's very important to take them out. So we take them out very often. So in 10 to the -1 neutron, it's the weight that is changing, it's not the energy. So the energy is a different parameter. The weight is how many particles are represented by this sample, one or whatever. It's an important difference. But imagine a low energy neutron in the shielding, in the concrete block. Now we have to not simulate absorption. We simulate implicit capture. So at every collision, we keep the particle and the weight changes to the surviving probability or times the surviving probability. So every particle lives on forever. So if you don't, that goes forever. So you have to terminate the pass in an efficient manner. If you don't do that, the calculation doesn't run. So it's a basic technique that you have to apply.
Okay, so let me cut here. Thank you very much, David. Next speaker is Villa Barancsuk from the Technical University of Budapest, and she will our grids on GPUs. Set it up. You can use also the technique. It's coming.
Okay, so thank you for the introduction. So today I would like to talk about the scientific application at the Budapest University of Technology and Economics. I'm an electrical engineer, so I'm not an expert in GPUs. And I would like to show you our research that we did and are still doing on the stability and vulnerability of power grids. My colleagues, so you can see on my presentation, have been working on this project quite some time now, and I just recently joined that project. So what we are interested in is how vulnerable power grids are, what are their stability measures, and how robust they are. And in order to investigate this, we implemented the Kuramoto oscillator model. Now you have to know that the Kuramoto oscillator model is a bit resource intensive. That's why we decided to introduce the GPUs into our project. Okay, so let's start with a quick recap on power grids. Sorry. How can I move the slide forward? Okay, thank you. Okay. So quick recap on power grids for those who are unfamiliar with these. Obviously, power grids are an essential infrastructure today for our civilization because they transmit the electrical power that we use for almost everything. Traditionally, power grids were primarily powered by these electromechanical generators. So these generators work in a way that they supply a bit of stability to power grids, but lately these power grids are under a lot of pressure because of, thanks to the spread of renewables. And these renewables, like solar panels or wind turbines, they are quite volatile, so they unstabilize the grid. Okay, so this unstabilization leads to the frequency of outages and blackouts growing lately. Let me tell you how we model the power grids using the Kuramoto model in order to investigate these outages. So the Kuramoto model is a system that can simulate all kinds of networks in the real life, and the Kuramoto model sees these networks as a set of coupled oscillators, meaning that it abstracts a real life network as a graph. And in terms of power grid, this graph is made up of nodes that correspond to, for example, substations and power plants, and even consumer nodes at the leaves of the graph. And the nodes, the edges of the graph are the power lines between these nodes. As I told you, the Kuramoto model has oscillators at every node that are coupled. And in normal operation conditions, the power grid, the power grid is node has roughly the same frequency under normal operating conditions. And in case of, like, for example, a storm or any irregular activity on the grid, this stable synchronized state can easily just blow up. For example, if there's a power line cut by a branch or by a storm, and this line failure, this line shutdown can then spread throughout the whole graph and cause like a cascade phenomenon and maybe a huge blackout or huge outage. Okay, so let me formulate the Kuramoto model mathematically. So on the slide, you can see for each node of the graph, for each oscillator. And as I told you, the Kuramoto model sees the graph as a sort of coupled oscillators, and oscillators are characterized by their phases, phis. And in order to investigate how stable the network is, how synchronized it is, we need to follow the change of these phis for each node over time, which means that we have to integrate this equation. For this, we use numerical solvers. And also you can see from the equation that each node space is mainly affected by the neighboring node spaces, as you can see from so each node is only affected by neighboring nodes. The A matrix is the admittance matrix, which is just a fancy word for adjacency matrix, essentially. And I also told you that there's a Kuramoto equation we need to solve for each node. And as far as power grids go, they can go up to tens of thousands or even millions of nodes if we want to investigate a more complex network. And in order to be able to follow all node phases, we introduced the GPU to start our investigation and our implementation from scratch. We already have an implementation. Our colleague, Dr. Kelling at Dresden, already have a GPU implementation of the Kuramoto model. And he also had a talk about it at the 2019 GPU Day. It's a very good talk, so I highly recommend it to check it out. The main points we have to know about is implementation, that it implements the second and the first order Kuramoto models, and we can use it for any graph we want. It abstracts the GPU using the Vexial library, and it already has a numeric solver for the equation from the Boost numerical library, but he only had the Runge-Kutta fourth order numerical solver, which is a simple implementation. And the main, I think the most interesting part of his work was the special memory layout he used to store the network graph for the GPU to efficiently access the data. I won't go into detail today, but you should check out his presentation. It's incredibly interesting. Okay, so, but in order to use his implementation, we needed to introduce some new functionalities into our system. For example, the most important one from these is the line failure modeling, which I talked about. When the graph desynchronizes, it can and we also use some higher order integration schemes in order to be able to tune the accuracy of okay. So that we integrated from summary. And I won't go into detail, but here on this slide, you can see the comparison of the runtime of these numerical solvers. As you can see, for example, that the BS, the Boolean store solver is the one that has the least runtime in terms of the overall benchmark runtime, which means that this is the best solver because all the solvers are tuned to the same precision. However, paradoxically, this Boolean store solver had the largest runtime per integration step, which is because it's the most complex of all the solvers. But it is able to quickly solve our problem. It is thanks to its complexity. It thinks a lot about what order to use, what integration step size to use, but then it probably makes the right decision and can quickly finish. Okay, so another the blackouts, as I already mentioned. So you have, in order to understand how power grids work, you have to know that power grids have these overcurrent line protection systems built into some of their substations and the nodes. And what it essentially does, it detects if the power flow between the nodes rises above a certain threshold level. And if that happens, it basically shuts down the entire line. Now this shutdown can, as I've already mentioned, spread to other nodes and then cause this massive blackout. I will just quickly walk you through how we try to simulate power grid behavior. First, we do the thermalization, which is just a warm-up process. We let go of the network and let it synchronize. And after the thermalization finished, it's in a basically in a normal operation condition. And then we perturb the network by removing a couple of nodes. And this removal is enough to, for example, start a blackout, start this line failure spreading all over the graph. And during this process, we measure important measures like the Kuramoto order parameter. So the Kuramoto order parameter shows us the overall synchronization of the graph. You can see on the visualization on the left side how a system can look when to the left it is fully desynchronized. All the phases are spread around from 0 to 2 pi. And if the network is synchronized, the phases gather together into close to each other. And in case of the synchronization, this Kuramoto order parameter is around 1. And in case of desynchronization, it's 0. Okay, so here you can see some preliminary results of our research. For example, on the left, we can follow how the order parameter changes during, for example, this one of the failure cascades. We also use different threshold values for cutting the lines. And as you can see, at the beginning, there are many lines that fail, but as we approach the end of the simulation, the system mostly synchronizes. I mean, not synchronizes, but gets to a steady state where the phases of the nodes doesn't really change anymore. Okay, we also I also plotted some other measures, important measures for different network sizes and different initial conditions. We still have a long way to go. So we still want to run a large number of parametrical studies in order to reach some conclusions about these power grids in terms of statistical physics and network science as well. Okay, to summarize my talk, I wanted to give just a quick insight into our research that was about the stability of power grids using the Kuramoto model to simulate the power grids. We already have a GPU implementation. We just introduced some new functionalities in order to be able to simulate power grids more. And okay, so this is the end of my presentation. Thank you for your attention, and feel free to ask questions.
Thank you very much. Questions, please?
Very good talk, thank you. So I'm wondering, with your simulation, you can analyze what happens if something fails. Is there any way to come up with interventions or responses to limit, for example, a cascade, to stop it getting even worse?
Yeah, unfortunately, if a line fails, it is not advised to switch it back on immediately. The best thing we can do is analyze the network statistically and understand which lines probably are the most vulnerable and come up with ideas on how to make these networks more robust in the long term. But immediately, no, we cannot really intervene. Gesa?
Just speak up, please. Yeah, maybe I can comment on this because our plan is also to study the spontaneous feedback. If you look at the Kuramoto, there was this dissipation term. This dissipation term is very similar as having spontaneous feedback. So we want to check what's the effect of spontaneous feedback. And in the later terms, we may also study
Other quick questions? I looked at one, maybe I didn't get the point. So what is one oscillator in reality? Is it a substation?
Yes,
or is it
it can be a substation, even a power plant. So these are of different
line
sizes.
is also, or the so passive line is a constant something, yeah? So it's part of the line. So I can imagine you can have a thunderstorm somewhere in along the line. So this means that you have the oscillators at a certain substations and nothing between.
No, any node. So nodes are any intersection between the lines where two lines meet, a substation or like a individual consumer or a transformer
so you have
station.
something like 4,000 or like that. What was the number of
nodes of so a typical power grid can be of varying sizes. It depends on the complexity of our model for the power grid, but it can go up to 1 or 1.5 million of nodes.
And there's a reality, for example, for Hungary, or?
Sure.
Oh, okay.
Yeah, absolutely. Yeah, we are planning to run this on Hungarian power networks. Yes.
Yeah. Okay. Thank you very much.
Thank you very much.
Thank you very much. topological simulation of resonant nano antennas for the nanoplasmic National Laboratory, which is at the Wigner Research Center. And we are very proud that we are using all devices for the topology. I hope you set it up.
Azt már csak elindítom, teljes képernyőn. Látják is.
Ezzel menjünk is ki.
Ezzel? Thank to apply for nanoplasmonic laser fusion experiments. The group is a big one. We have a theoretical group, which I'm in, the material group prepares, and the spectroscopy group who then analyzes the results the laser group did. We try to go on a path achieving thermonuclear fusion. The idea in fusion is that the hydrogen atoms then fuse into helium. They release a big amount of energy due to their together they are heavier than the helium, and to have it in a reactor and to use it for energy production, certain criteria have to be fulfilled. I will not bore you with the details, but there is a gain factor, and this gain factor says that at a critical level, the confinement time and the density of the plasma gives two approaches: magnetic confinement, which to have a working power plant, and inertial confinement fusion, which increases the density of the target. Our aim goes in the direction of inertial confinement fusion. There are two types, direct and indirect type. Ours will be direct because we do not have we shoot the target directly with the laser. The most advanced type of fusion here is at the National Ignition Facility. They use an indirect drive. They shoot a gold nanotube with 192 or 992 laser beams which then evaporates and produces X-rays, and the deuterium tritium ice is inside a shell. Earlier days there were plastic ablators. Nowadays they are using high density carbon, and as X-rays evaporate the shell, as the shell goes out, it compresses. Earlier days, the problem is that it is not a symmetrical compression, and this case results in Rayleigh-Taylor instabilities because the inner layer is more dense, and as you can see that they needed much more density. Later, the latest news in August, that they reached 1.3 megajoule kinetic energy. This was in 50 or something kilojoules, but they still have a burning time of 130 nanoseconds. We aim to minimize and actually to avoid the Rayleigh-Taylor instabilities, and this is a spin-off from heavy ion collisions, where in the quark-gluon plasma at the hadronization phase, you can observe a time like oops, sorry, detonation. So the time like means that atoms are excited, and energy is not given by the neighboring atom, but they get excited first by the laser beam, and then they ignite together independently from one another. So by the time the other laser beam reaches, they can ignite. At a constant absorptivity level, when the target has a constant absorptivity everywhere, then this time-like effect is very small. So 12% of the target ignites in this way. However, another idea came thanks to Kronorbert, who is working with nanoparticles, that we vary the absorptivity of the target depending, as we go inside the target, doping with nano antennas, gold nano antennas. These gold nano antennas have the effect that they resonate, and they can at this resonation they can absorb more energy, and doping with gold nano rods, the absorptivity, as the absorptivity increases, it can be seen that this the amount of burning material would be around 73%. Our concept is to have two opposing laser beams and a cylindrical shaped target, laser beams coming from this direction, and to minimize the surface of the target. So we should have the minimum surface for a volume. And the deposited energy at a constant phase out. However, if we have an absorptivity that looks like this, it is a Gaussian-like shape, then the energy that can be deposited goes very deep inside the target. So since we have to achieve fusion, the particle in cell method was chosen. This is the method commonly physicists. The idea is that in a particle in cell method, on the cells we have the fields on the edge of the cells, and the particles move freely. This is a finite difference time domain method, which solves the Maxwell equation. So for earlier, we use this epoch code, which is written in C++, and this is the method that we calculate the fields in half steps. Then we have a particle pusher, which calculates the currents, and then we use that to calculate in the next half step the fields. So this is the particle. Have a shape, so they for the most simple one is triangle shape. 50% of the marker particle is inside the cell, and the other 50% of it is in the neighboring cells for one dimension. This is the first of the approximation, yeah, and so the nanorods finite difference time domain method. However, they cannot use they do not use electrons, so they cannot effects when the nanoparticles are below, for example, 20 nanometers. This the plasmonic effect which we use is the enhancement inside the target, so the energy absorption is enhanced. And in the classical case, the field solver, this gamma is a damping factor. In cell method, we can have the collisions. For example, in the epoch code, there is a built-in collision simulator, which is from Nambu and Perez. So the nanoplasmonic effect is due to the collective motion of the the conducting electrons, and for golden nanorods, for example, in vacuum, this empirical three-parameter equation was a result, and this and for example, this in vacuum, half of this wavelength is the resonant nanorods length at 25 nanometer diameter. So we simulated this inside the particle in cell with as we put also gold ions. Show you just a second the movie. Does it work? Okay, this doesn't. So then I will show. Actually, the movie shows the vibrations and also that the gold nanorod is shrinking because we have the electron spilling out, and this resulted in vacuum a 66 times higher and so in conclusions, these models qualitative description of these nanorods. However, in future we will have to combine both approximations because the absorptivity increases is slightly lower than the experimental results. We also this is also an approximation where we do not have for fields we calculate in spectral space, and this will be our next project because implementing in GPU the epoch code was slightly tougher. Load balance requirement. So the load balancing was very cleverly solved in the epoch. And thank you. Yes, sorry for that.
Questions?
Future. Okay, so with this, the laser comes at 28 femtoseconds. It is a step function laser corrected with the cosine edges.
So that is the okay. In simulation, you simulate electrons.
Electrons and yes, gold ions. and gold ions are so large, and we have 3 times as many electrons.
Are these the ionization self-consistent, or do you assume an ion distribution?
We assume an ion distribution inside the region of the nanorod. So the number density outside of the nanorod goes to 0, and inside we have the number density of electrons of 10 to the 20 power of 28.
Plus an extra result.
Yes.
Okay. So I can see this sense. So thank you very much, István. István Reguli from the Science paper, Catholic University, and we will speak about accelerating field.
Yeah. No videos.
Okay, thank you very much. I'm here to talk about tri-diagonal solvers. Semester of university. We have a linear system, and in tri-diagonal equations, what's special about this is you only have non-zeros on the diagonal, and then one above and one below the diagonal. And so hopefully everyone remembers that linear systems like these are usually or can be directly solved using the Gauss-Jordan elimination, which first goes and eliminates values below the diagonal and then above the diagonal until you get basically one. And so with tri-diagonal equations where you only have non-zeros here, this becomes a little bit simpler, and it actually has a name. It's called the Thomas algorithm. It is an inherently sequential algorithm. It basically implements this Gauss-Jordan elimination, and as such, it has order n complexity, so basically the number of unknowns. And this gives for this equation. Come up in for example, finite difference discretizations of PDEs, partial differential equations, and lots of other places too. Basically, you can either solve these things implicitly or explicitly, and this is the implicit version. So is the algorithm called the parallel cyclic reduction. The idea here is you for each row you subtract the row above and below, thereby pushing your non-zeros outward, and you keep doing this until you basically push them out of the matrix. So ultimately, you would be subtracting the rows above and below, then too far away. Can actually be done in parallel, because you can do this for each and every row at the same time. Then, of course, you do need a synchronization point. Then do it in parallel for the too far, then 4 far, etc. So this is order n log n steps, but the n bit can be done in parallel, assuming you have that many steps.
So while computationally slightly more expensive, there is a log n multiplier in there, it is more parallel. And what you can also do is chop up your matrix into blocks and still use either Thomas or PCR or whatever you really want. Would give you a dependence on values that are just outside parallel. You will have to do some sort of communication. You have to do a solution on these interfaces between the blocks. And so what you usually do is then you big as many blocks you have, and then you substitute your answers back inside of the blocks. And so this again is, of course, the order is conveniently hiding some important multipliers or factors there associated with the reduced system solve. So this is particularly useful in shared memory systems, where, for example, using CUDA or OpenMP, you can come up with independent and trivially parallelizable chunks of work. And this is particularly systems. Then, this part of the system is sitting on one GPU, this part is on another, etc., etc. Now, to make things even more complicated, we rarely have these single equations by themselves. What we usually have is many of these equations that come together. So, for example, you can imagine even for 1D PDEs, in computational finance, you want to run different of slightly different scenarios, each of which gives you a single tridiagonal system. And for more complicated problems in 2D or 3D, you're working on higher dimensional problems, and depending on your problem, there is a nice implicit solver method called ADI, alternating direction implicit, where the idea is for a 3D problem, you would do one-dimensional solves iteratively, one after another. What you have is your data is laid out in 3D, and depending on in which direction you're trying to do the solution. So in the X solve, what you would do is coefficients along this axis would form or would represent a single linear system, and then this row would represent the second linear system, the third, the fourth, fifth, etc. So if you have such large problems, especially for computational fluid dynamics, let's say you're trying to simulate, in our case, or the motivation for some of this work is large fields of wind farms. You'll have thousands by thousands to chop this up and assign different little blocks to different GPUs or different CPUs, etc. And then you have this situation where you want to do solutions along various axes. And so you're in a situation where you naturally have this sort of block decomposition for each and every system. And so within each partition, let's say each GPU, you could decide which solver you want. So within each of these blocks, you could do PCR, you could do Thomas, you could do a combination of the two.
And then you would have to do this reduced system solved for the unknowns on the interfaces of these blocks. One option there is that process reduction on the reduced system itself, so only these bits, which means that each process will talk to its neighbor. So this will result in having multiple smaller messages to increasingly distant neighbors. And you can also do an approximate solution with, let's say, a simple Jacobi iteration, in which case you will only talk to your immediate neighbors, but not just once, but until you converge to some sort of error. And this can be shown analytically that depending on the condition number of your matrix, it will converge pretty quickly. So we went and implemented all of these and tested on CPU1 is Archer 2 in the UK. These have the AMD EPYC Rome CPUs, 2 of them, each with 64 cores. And we also looked at Cirrus, which is a smaller supercomputers with each node equipped with 4 V100. They can talk to each other pretty quickly. And then we compare our library to an already existing established library called TriDiagal-U, although that library can only do MPI, so there is no shared memory parallelism, which incidentally means that your reduced systems become larger. So in our scaling tests, for strong scaling, we solve a 512 cubed problem and then throw more and more compute resources at it, see how faster we can get. Or for weak scaling, we keep this problem size per node constant. And whenever we compare exact solutions using these all-gather or PCR reduced system solvers to iterative solvers using Jacobi, we'll be using 10 iterations for the iterative solver. So baseline performance on a single node or a single GPU, we achieve a pretty reasonable fraction of bandwidth. These algorithms are all limited by how fast you can move memory between your CPU and the main memory. And then even higher for the GPUs. I should note that there is a bigger variability here. GPUs particularly suffer from x-directional solves, where data is not laid out in the best way for GPUs to read them. Okay, so what does performance look like on the CPU? You can see 2 bunches of lines here, the full ones and the empty ones. The difference there is whether we're using Jacobi or PCR for also visible up here, the slowest x directional solve. For PCR, initially, the overhead that comes from the reduced system solves is very little, but of course, as you scale up to 120, the communication also grows because you have to talk to even farther processes, and so it sort of increases. Whereas with Jacobi, you only talk to your immediate neighbors, and so scalability is slightly better. And we can see very, very similar effects on the strong scaling. side of things when we're trying to solve a single 512 cubed problem on more and more nodes. And then here we are comparing a few more specific cases of how we solve these reduced systems. These lines which just go way off, these are the all gather solutions where these reduced systems are gathered onto each and every process, and that ultimately just results in an exponential explosion of communication. So it's not something you want to do. But PCR and Jacobi are both scaling very well. PCR gives you an exact solution, Jacobi on only an approximate solution, which in most cases is more than enough. And the two interesting things to compare are different in how we do communications between GPUs. We either make explicit copies on the CPU, and then the CPUs talk to each other, or we use something called GPU Direct, where the GPUs can talk to each other directly, well, more or less. There is a somewhat lower overhead here. Here you can see HC would be host copy and GD would be GPU Direct. And particularly for the all gather cases which move a whole lot of data, the GPU Direct performs significantly better. This is working pretty well and faster than the host copy versions. Now, a few points about FPGAs. On FPGAs, we usually want to solve systems are much smaller. In 2D, you would do 32 to 128 squared. In 3D, 32 to 296 cubed. And then you would have a few thousand systems to solve in 2D and a few dozen in 3D. You can also solve problems which do not fit in the FPGA in the VRAM, and then use this blocked approach. To give a performance model and try and figure out whether Thomas or PCR is going to perform better on the FPGA. And so based on the number of multipliers, divisions, subtractions on the two different algorithms, we came up with this simple the Thomas algorithm to solve a system, or the PCR. And so because Thomas is inherently serial, one iteration of the forward step is about 30 clock cycles on a Xilinx U280. On the PCR side, you can, since PCR is parallel, you can parallelize within the solution, so you have this FU unroll factor. But of course, that on the FPGA consumes more resources. Then architecture, so you can have as many systems as long your pipeline is in flight at the same time. And then on top of this, what you can do is vectorize your solvers. So you can have, in our case, 8 systems at the same stage of the solution, not just in different steps in your pipeline. In some data layouts, this is easy because data is right there next to each other. In other data layouts, this is not so easy, so you have to do a sort of on-the-fly track. So we compared this to an already existing implementation in the Xilinx Financial Toolbox or something it's called. And while at really small sizes, it does perform better than our implementation. As we go larger, it becomes, I mean, our solution becomes a lot fewer resources on the FPGA, which of course is a pretty relevant factor there. So looking at the 2D and 3D problems where you want to implement alternating direction implicit, so solves in various directions. We looked at 32-bit as well as 64-bit number representations, and we see that the predictions are pretty accurate. Beating the GPU, a V100 GPU. And so for reference, we also have some energy numbers here, how many joules were consumed during the solution of one large system. And again, the FPGA is significantly better. Now, this is more of a toy problem. This is a full proper financial problem with multiple stages of computations that compute the coefficients for these systems. And so here, the benefit on the FPGA is no longer that large. In small systems, you're still much faster than the GPU, but that's partly because the GPU is insaturated at this point. For larger systems, you are within a factor of 2, but in terms of energy, on the FPGA or the GPU, there is still a 1.5, 2x improvement on the FPGA. So in summary, we looked at various kinds of parallelizations of tridiagonal systems, how you decompose them, how you solve collaboratively on multiple CPUs and GPUs. And we saw that this can indeed scale pretty well, despite this being a proper full implicit solver. And we also saw that we can do this on the FPGA for smaller problems that is very, very competitive with GPUs. Thank you.
Thank you very much. So does it have any specification for this GPUs what you have used, or it can be turned to any kind of other GPU types?
We tested these on Teslas, so back in the old days, Keplers, and then these results are from V100s, but I've also run them on A100s. I think there is no, there. So we only looked at this, so we are using Vivado for writing this, and I think that may be Xilinx specific, but this could be equally implemented with OpenCL and on an Altera Intel. So yeah.
So it's much higher due to the uncoalesced access if you're accessing around
the wrong direction.
The wrong direction. And that's typically for image processing. I think it's solved by just transposing.
Yeah, that's exactly what we are doing on the GPU as well, but it does have an extra cost, and that's why it's slightly slower than the Y and Z solves, but it's nicer immediately. Yeah.
And how does your GPU implement? Diagonals or the spike? Is a variation of PCR or this PCR?
Hold on. Okay, so there is cuSparse, which implements, I think, some variation of PCR. cuSparse is tuned for either really large systems, a single system, and it also has a batched solver, but it either so if you are in 3 dimensions, you can do X solves and Z solves, you can't do Y solves. The API is just not equipped to deal with non-uniform strides between systems. For the X solves, Q-sparse is slightly faster, 10%. For the Z solves, we are faster, about 15%.
The very last question.
Okay, so at least for the 2D case on GPU, did you try using the texture memory instead? Because it normally doesn't store it in scanline order, so it should have seen gains, like, you know, from thinking their own patterns and actually transport it.
Yes, so we started this work on Keplers, and we did start looking at using texture, although not sort of explicitly as those texture objects, rather just the const restrict blah blah blah, which then brings in memory through the texture cache. But still the LDG load. But still the transpose in either shared memory or registers with these warp shuffles that turned out to be faster.
Yeah, sure, but that's because the texture objects store in different order, so it doesn't only change the caching.
Okay, but then you would have a cost involved in right. Okay.
Okay. So thank you very much.
Thank you.
Nice talk. Lunch. So please follow Balázs or Gabor. You will go underneath, and there's a restaurant. And if anybody asks you about the conversation that you and the speakers of the message.
Most be van kapcsolva a mikrofon, akkor hallható vagyok. Szuper.
Igen.
Akkor minden készen áll.
Gondoltam, hogy akkor figyelem a kettőt. Ez csak a Zoom-ot, ez csak a YouTube-ot. És akkor hoztam még egy monitort, adtak még egy monitort, tudod, és akkor csak átadtam. Igen, de én meg csak figyelem, tehát nem avatkozok be. Ezért is láttam, amikor úgy megfagyott, vagy fagyogatott.
Az le van fagyva.
Ez előbb láttam.
Most.
Az késik.
Nem, a Zoom az nem késik.
A Zoom az nem késik.
De az is egy ilyen pár másodpercre le tud is fagyni. Jó, amikor arra fele van fordulva az ember,
Hi, Visca. This is Gergely speaking. Can you hear me?
Yes.
Ah, perfect.
Can I swap with Laszlo?
Of your microphone.
Megnöveltem a hangra.
Yeah, speak a bit just to see whether we can hear you.
Hi, my name is Visca.
It's
Is that okay? Why is
Can you share your slide? Well, yeah, no, we can put this. I think so. Do you really want to switch over?
Yes, yes.
Because now you are online and we can just have easier 1-2 minutes delay and then you can make it. But I'm not sure that you can be still online with after the. I mean, up to you. You can switch over if you wish.
Oh, I do want to switch over.
Okay, so then let's will start. Okay. Then please mute your microphone until the. Yeah? Okay. So welcome back, everybody. Very well. We are jumping to the second part, the afternoon session. Now you are fully relaxed, so I hope you will also enjoy. There's an immediate change because we have one of our speaker is online now, and we could just manage to have online, but just to be safe, so we switched. So now we are going to go to László Dobos first, implementing the hierarchical Bayesian networks on GPU, and then we will have Visca, which is somehow connected to this work as well. So please, Laci.
Yeah, so we are working on the same project, 2 sides of the same project. Going to talk about astronomy, not actual hierarchical Bayesian networks. At least I'm not going to go in astronomy. Is more interesting? It doesn't work. So the project I'm working on with my colleagues at Johns Hopkins is a Japanese project. It's a new spectrograph for the Subaru telescope, which is situated in Hawaii on the Mauna Kea. And the one on the left is the Subaru telescope. It's an 8.2 meter telescope. And now an international team is building this so-called prime focus spectrograph for this telescope. And it will be able to do low and medium resolution spectroscopy from the infrared, near infrared, to the visible blue light of the electromagnetic spectrum. One is that it has a large mirror, so it's an 8 meter class telescope. There's only a handful of those around the world. And it also has, and this makes it unique, a large field of view. So we see a significant part of the sky, about 3 times the diameter of the full moon when we use this telescope. So this makes this instrument very unique for those observations that we are planning to do. I want to talk about that. So this is the Subaru telescope. This is huge. So the mirror diameter is 8.2 meters. So this whole structure from bottom to top is about 20 meters. It's large. And the prime focus spectrograph goes up here. So this is the prime focus of the telescope. Here's the mirror down here. So this whole instrument goes on the top, and it's going to going to be consisting of these fiber positioners. So the way it works is that the light gets reflected from the mirror, it gets to the fibers will be terminated up here with these fiber positioner mechanics. So we'll be able to automatically position the fibers to the objects we are interested in. So within a petrol radius of each fiber, we will be able to choose which star or which galaxy to observe. And this whole thing can be reconfigured to different objects in about a minute. So while we are doing the observations and we decide to move on from one object to the other, it will be possible without basically taking the whole telescope apart. And this will have lots of advantages. And actually, this is where most large room for optimizing the observations. And if there's a large room for optimization, then machine learning always comes in. So this is the frame that will hold these fiber positioners in a hexagonal setting. It's going to be pretty large. And this is one of the cameras. Again, this is in the lab. And I saw this myself, and it's about this big. So this is just one of the cameras, and there will be 12 of these. It's currently being built in Baltimore and Johns Hopkins. And there in parallel at the same time.
What does it mean to position these things? So
yeah, so you take an image of the sky, right? We already have those images, and then you find the objects that you want to observe. Actually, this is what I'm going to talk about. So what are the objects and where you want to position your fibers.
But the fibers are fixed?
No, the fibers move around on these positioners. Okay, so you can position a fiber on any of the objects you want within the fiber radius. And you have 2,400 fibers to allocate over the object. And then we do observations in 15-minute increments. Okay, so the project that we are working on is called galactic archaeology. So we are looking for very old things with the intention of understanding how stars we are going to observe the local universe, so not distant galaxies as other sky surveys do, but we are interested in individual stars. So we will try to find and observe spectra of stars in galaxies other than the Milky Way. And these will be satellite dwarf galaxies orbiting the Milky Way and also the Andromeda galaxy. That's close enough that we can see the individual stars, only the brightest stars, but we'll be able to observe those. So we are interested in the formation history of the Milky Way. And for instance, we'll be able to observe, if you look at the background, it's a little bit dim, but here's the Milky Way, and there are satellite galaxies orbiting the Milky Way. And when they gravitationally interact with the disk of the Milky Way, teams are formed of those very, very old metal poor stars that the satellite galaxies are composed of. So when we observe these and the exact kinematics of these stars, then we can reconstruct the dark matter distribution within the Milky Way. Okay, so just a few basic things we can observe. So when we do imaging, photometry, we see the apparent bright. Very high resolution, then we can always measure the 2D position of a star on the sky. If we have high resolution, we can measure the 2D velocity of these stars. And some satellites can also measure distance, but we are not relying on those because we are looking for faraway stars. And this is not enough to do galactic archaeology. to do galactic archaeology, one needs spectroscopy because we also want more precise temperatures. We want the so-called gravity. So gravity is the gravitational acceleration at the surface of the star, whatever the surface is. It's not a solid surface, of course. How dense the star in the photosphere, and this is to tell red giants from red dwarfs. I will explain briefly what these are. Okay, we can measure the metal content, and the other important quantity to measure to reconstruct the kinematics of these stars and their interaction with the Milky Way and the dark matter distribution is radial velocity. It's called radial velocity because it's the line of sight velocity. And we can measure it from Doppler shifting of the spectral lines. So this is what we are shooting for. And of course, we will need to skip these, it's not that important. So this is how a red giant like our sun, or even smaller mass, lower mass star, which is even redder than the sun. And red giants are stars which are very voluminous. So they are large in size, but not necessarily in mass. Okay, they are so-called evolved stars. So if we look at theory, and we have some estimate of their sizes, then we see that the red dwarf is about this big, and then the red giant is this big. So it's much brighter. It produces a lot more energy, but it has the same temperature, surface temperature. Of course, they have very similar mass. It's just that the red giant is a little bit older than a red dwarf. But if we look at these through the telescope, and the red giant is in a satellite galaxy 100 kiloparsecs away, which is, I don't even know how many light years, but outside the Milky Way galaxy, and the red dwarf is within the Milky Way galaxy, somewhere in the vicinity of the solar system, then they will appear exactly the same in the photos. Okay, so if we want to pick which one to take a spectrum from, it's a challenge. Okay. This is where Bayesian networks will come in, because we can tell all kinds of probabilities of being a red giant or a red dwarf. Okay, I'm going to skip this too. So this is how we tell from spectra, which dwarfs have a dense atmosphere, so the spectral lines are broader due to broadening from pressure. Okay, if it's a red giant, the red giants have very low pressure atmospheres, so the absorption lines will be much thinner, narrower. Pick which star is which from photometry on.
And the content is always the same or different?
It's usually different, but you can't really disentangle it from the age if you just look at photometry. There's a degeneracy that you can only resolve with spectroscopy, or also narrowband filters, but I'm not going to talk about that. Now, this is how a dwarf spheroidal galaxy looks like. It's one of the satellites of the Milky Way. It's the Sculptor galaxy. As you can see, it's a slight overdensity on the sky. So you can clearly there's something here, because the density of the stars is larger here than here. But if I show you a tiny orange dot, can you tell whether it's a red dwarf or a red giant? No. Okay, it can be in the foreground, or it can be a member of the satellite galaxy with some probability. Of course, the probability is higher here in the middle because the satellite galaxy is denser. probability of membership, but the probability of membership here is much lower. But being members or being foreground stars, then we have to decide which ones are interesting enough for a spectroscopic observation and how much failure rate we can accept. Because sometimes we will put a fiber on a star and it's going to turn out as a foreground dwarf that we are not on these large telescopes. So we want to optimize the observations. So this is how astronomers look at the images. Okay, so what I'm showing here is a graphicon or calculated from the brightness measurements of two different difference of the brightnesses or the ratio of the brightnesses. This is what we get if we analyze the images of a satellite galaxy. And what you can see here is that the color is roughly the equivalent of the temperature, and this is the brightness, so the brighter stars are toward the top. And interestingly, these stars, which draw this nice track on this color magnitude diagram, are all members of the dwarf satellite galaxy. And that's because these stars are all at the same distance. Okay, so they follow, their brightness follows the theory nicely. All the stars that are scattered vertically are members of the Milky Way, and they are at very different distances. So they just nicely fill up the foreground on this color magnitude diagram. Now this track here is called the red giant branch, and these stars are all red giants. And then everything else is just different components of the Milky Way, which have a very distinct distance distribution. Okay, we don't care about those. We want to target these stars. But of course, this red giant branch, which we stars, and we want to get rid of. If we look at the theory of stellar evolution, if someone tells me what the metal content, the initial metal content of a star, its mass at formation, and the current age of the star, then I can tell how bright it is in the different color filters. And these results are calculated and tabulated in so-called isochrone tables. Okay, so I need to interpolate these isochrone tables, and then for any combination of these physical parameters, I can calculate the magnitudes of the star in any filter system that we have. Now, what if I want to do it the other way around? So I observe a star, I know its magnitudes in each of the filters. How can I tell the physical parameters? I have to invert these, but these functions which convert the physical parameters in valued sometimes, and it's just very messy. Okay, so inverting these is in itself a problem which can be solved with Monte Carlo methods. But we will go a step further, and we want to stellar populations that we see. So what are those stellar populations? One stellar population will be the members of the satellite galaxy, and then different populations of the Milky Way, like these are the Milky Way disk stars. This part here, the blue part, is the Milky Way halo. So these will be the populations that we take into account. Now we have to make more assumptions, and we are going toward the Bayesian model, because we'll talk about priors here. So we know quite a lot about the Milky Way. So we know that it consists of different stellar populations, like the disk and the halo. Distribution of these components. Okay, so usually the density of the stars decreases exponentially as we go further out from the center of the Milky Way. Now we also know about the metal content distribution of these stars and so on and so on, also their kinematics. Mass function of the stars. So the mass function basically tells when stars are formed in a gas cloud, they are formed with different masses. And we know this distribution of the masses. This is very important for this whole Bayesian analysis to work. Okay, and we also know that the dwarf galaxy member stars are at the same distance. They are very far. And we have to fold these in. And this is where we can build our Bayesian mixture model. I'm not going to write formally, but basically we have to calculate the posterior probability for each of these stars being members or being non-members, where membership means member of the dwarf galaxy. And this turns out to be a mixture model in Bayesian statistics, which is a little bit tricky. And it poses lots of challenges. Of course, it's computationally intensive. That's going to be one of the challenges, but there are mathematical challenges that we haven't really solved yet fully, because it involves sampling categorical variables, so non-continuous variables. That's the membership star. And okay, so how do we construct this Bayesian model? We have some rough assumptions on the weights of the populations. We have priors for each of the physical parameters of every star. So what's the distribution of the mass? What's the distribution of the age, the metal content, and so on and so on. And for each population, we have these distributions as assumptions. And of course, we want to fit Milky Way. We know most of these parameters, so we can just plug those into the model. But for the dwarf galaxy, we want to fit the mean age of the stars in the dwarf galaxy, or the Bayesian models can do this. What they can't easily do, or not well documented how it should be done, is when we mix populations together and then we want to get the population memberships. Okay, so we also fit the population parameters, as I mentioned, but as a byproduct to all of this, for each and every star, we will have the posterior distribution of all the physical parameters. So we'll be able to tell for each star that, assuming it is a member of the Milky Way, its mass is a little bit higher, okay, or its age is a little bit older. And we can do this for 100,000 stars in parallel, and we have to do this for 100,000 stars in parallel. So just imagine it. So when we are solving this Bayesian mixture model, it's like a Monte Carlo on a million variables in parallel. So this is basically the problem we are trying to solve. Of course, it's a tricky Monte Carlo because it's interleaved. So the individual stellar parameters need to be stepped or evolved in every step. And then we have to switch to the population parameters, and then we step the categorical membership variables. So it's within a Gibbs sampler. So it's a tricky hybrid Monte Carlo sampler that we had to put together. Because talked about that distributions that we know, but none of those distributions can be easily described analytically. So we have everything tabulated. And this is, because of this, it's very computationally intensive. And this is unfortunate toward analytic problems. So we couldn't really reuse those. We had to rewrite everything basically from scratch. Not Monte Carlo sampler, but unfortunately those didn't work. Okay, so we have three types of numerical problems that we have to solve on a large scale at every step. Of course, we have linear algebra, small matrices, but 100,000 of those. We need to be able to very quickly randomly sample variables for all kinds of distributions. Some of these distributions are tabulated, and we want to avoid rejection sampling at all costs because that's very pricey. And we need to do isochrone table interpolation. That's a pretty convoluted iterative method. So it's not a linear interpolation. It's a lot more than that. And so once we get the memberships, we will get plots something like this. And this is a logarithmic plot. So the red is high probability members. White is around 10% probability of being a member. And then blue is non-members. And these are the stars that we want to target. And actually, it's an interesting problem. If I have a minute, I will try to explain this, because we want to find the stars which are members, but that's not enough, because we want to optimize this whole targeting algorithm to answer scientific questions. So we want to target stars which are very likely members, which are bright enough to measure the physical properties from the want to optimize for a subset of stars that can help us answer questions like what is the distribution of the dark matter in a satellite galaxy. Okay, these are hard optimization problems. We don't optimize. Choose which subset of the stars to observe together in order to answer the scientific questions. So we optimize for the scientific gain, and we are willing to take risks. So we will observe stars which are only 10%, which have only 10% membership probability. But if we succeed, star, it will just bump the utility of our observations a lot, because we will be more likely to answer the scientific question at the end. Okay, so, and let me stop here because a little bit about the implementation details. So this whole thing is implemented in TensorFlow, but we use eager mode. So TensorFlow is originally for deep learning. There's no deep learning here. And because none of our distributions are actually analytic, we can't even benefit from the fancy features of TensorFlow, like automatic differentiation. We don't use that. But it's still a nice programming environment for the GPU. The other one being PyTorch. For some reason, I ended up using TensorFlow. Of the execution into execution graphs instead of running in eager mode. So it would be a little bit faster, not significantly. And we had to implement this adaptive Monte Carlo sampler from scratch, but we could rely on high-level probability package, which has a very nice tool set for generating random numbers, for example. And it requires a pretty big card, because we are running it on Tesla V100s with 12 gigabytes of RAM. About half of the RAM is used for solving one of these problems. And one of my current problems is that eager TensorFlow doesn't support multiple GPUs at the same time, which would be great, but that's not available at the moment. So we are waiting for that. And I'll leaving this slide here, and I'm happy to take questions.
Thank you very much, Laci. So you mentioned the beginning the distribution, so the mass distribution of the stars.
Yes.
And and also so how it distributed within a galaxy. And
yes.
Do you and in the very beginning you mentioned also that this can be some relation to estimated dark matter or dark energy, dark matter mainly. So what is the relation for this Bayesian selection if you would miss the mass distribution of the
the mass distribution, it has no relation to the dark matter. At least we think it's universal. So the initial mass function, as it is called, is the now wherever we look, it appears to be the same. So where we can connect this to the dark matter is the motion of the stars, because the dark matter basically controls the motion of these stars. The Doppler shifts, basically, that's what tells us what the underlying dark matter distribution is.
Okay,
so that's why we have to optimize for a set of stars.
There's no effect of this on the Bayesian and the selection document?
Well, you can do it at many levels, but of course it can have.
Yeah.
It can have. So at the end, when you optimize the observations, that's why maybe Alex will talk about this tomorrow at the workshop. Mm-hmm. But so the dark matter halo profile at the end, then you have to target specific stars, and that's where you have to take risk to observe stars which are likely non-members, but you need those stars in order to constrain your model.
Yeah.
Okay, so this is where it becomes a hard optimization problem.
That partly answers my question. You said that you are optimizing for scientific value, and that's a vague problem. And you said that the properties you're interested in is whether it is a member of the population and whether it is bright enough to actually see something of it. Are these the only two? Or
so what you call the vague is that, just imagine this. I have these stars, I know the membership probability. Okay, so this is just step is we have the probabilities, but we also have a model that we want to fit to the data. Okay, and we want to observe stars with the constraint of knowing the membership probabilities so that we can fit our model. This model fitting is another tricky Monte Carlo code that we want to run.
It becomes a tessellation problem with some weighted value, not just overlapping, but some other weights.
It becomes a difficult problem. And then there's the problem of assigning the fibers, which is another. So there are these very tricky optimization problems.
Final question. So do you have a standard candle like
standard? Yeah, because the tip of the red giant branch. Okay, so the brightest red giants can be considered pretty stable standard candles.
Oh,
yeah.
Okay.
So you can use, if you find them.
So that has the 100% probability.
100% probability will be unlikely. Okay. The probability of the probability will be low.
Okay.
All right. Thank you.
So thank you very much, Lester. It was a very nice. You can come over. I need a little bit of help. So Viska, are you still online?
Yeah.
Oh, great. We can stop share. Yeah, stop share. And would you please try to share your slides?
Okay.
Maybe you can show yourself for the audience just for a second. Thank you very much participating. As you are in the East Coast, so it's pretty early for you. And this is a kind of pajama party. I mean, So the next speaker is Viska Wei from Johns Hopkins University, working together with Laszlo and Alex Salai, and the title is Artificial Intelligence Applications in Stellar Spectroscopy. So please, Viska, you have 25 minutes.
Okay. Can I start?
Yeah.
Okay. So my name is Viska Wei, and today I will present my group's results on AI application in stellar spectroscopy. But Laszlo already covered most of my parts, so we'll see. The stellar spectroscopy studies the spectrum of stars. So to get the spectrum, we use an instrument called a spectrograph. A spectrograph is a very powerful prism we put in telescope to split the light and get the spectrum. This is the spectrum of a red giant. Stellar spectrum encodes rich information. We cannot only derive physical properties like the temperature of stars, surface gravity, which is the compactness of the star, and it can be used to separate giants and dwarfs. We also get information like radial velocity, the velocity of stars that with respect to us from Doppler shifting. We can also learn the markup of the stars, like the metallicity, element abundances, such as the carbon, oxygen, or iron percentage in a star. The prime focus spectrograph is one of the newest spectrograph under construction. It will be the largest and the most powerful telescope in the world when it sees the light next year. The Subaru 8.2 meter telescope is one of the world's biggest telescopes located on the summit of Hawaii. The prime focus spectrograph will be installed there. So why is the worldwide astrophysics community building this $80 million spectrograph? The people building this instrument are designing a survey with scientific goal includes like the structure of the Milky Way, the evolution of the galaxy, and the distribution and the properties of dark matter. My project is on the galactic archaeology part of the survey. On one hand, we trace the history and the formation of the Milky Way galaxy by targeting the satellite galaxies that helped form the Milky Way during early stage of the universe. The stars there are very old and high value, but the problem is that they are far away. Only a tiny portion of light reaches our telescope, so they appear to be very faint. On the other side, we aim to profile the dark matter halo that is believed to be enshrouding the Milky Way as shown in the figure. Therefore, be able to see much more stars within the same amount of time and be able to see much fainter stars help tremendously. The Subaru telescope can see fainter stars because it has a huge mirror and thus collecting more lights. And the spectrograph has a wide field of view, which can cover much larger area in sky and see more stars. So in short, this $80 million is a must and a best for our task. One of the great challenges of designing the survey is determining exactly which astronomical objects should be observed with a spectrograph and how long each should be exposed. The longer the exposure time, the stronger the signal to noise ratio, which gives us more information about the star. But we want to spend it on good stars. We want to spend it on high value stars as time is the most expensive factor. For example, when we target the satellite galaxy, we typically observe the luminous red giants in it. The figure on left shows their size compared to the sun on the log scale. However, when we observe the giants within the Milky Way, we see lots of dwarf stars, which happen to look the same. Although there's like a huge difference in their size and the surface gravity, they're both red, and the further away giants will look smaller and fainter. So inevitably, we will observe large portion of dwarfs that are not member of the satellite galaxy. That is the membership problem Laszlo was talking about. And the only way to tell them apart is using spectroscopy, as their spectra contain information about the surface gravity. However, it is hard to tell. This is what we see after a couple minutes of exposure. It's very hard to tell because of the noise. We have to keep looking at the star for several hours longer, because the longer the exposure time, the stronger the signal to noise ratio. And traditional methods takes hours to fit the physical parameters of stars. To be clear, it takes hours to get a spectrum, and it takes a couple minutes to do the parameter fitting of the stars using chi-square and similar methods. But the 80% of targeted stars are not interesting. The power of estimating the value of star from raw noisy spectra is highly demanded. And I don't want to stress you out, but it's an $80 million instrument, and it costs $100K to operate per night. We have less than 100 nights of telescope time. As Laszlo explained, the spectrograph has 2,400 fibers, meaning that we can observe 2,400 objects simultaneously, and we can move any one of the fiber to change target anytime. Here's some early stopping criteria that we want to apply to filter out unwanted stars. First, is this target a member? Like if it's the foreground dwarf instead of the target giant, we want to move on. And second, if after long exposure, the noise is still too large, we don't want to observe it to begin with. Like we don't want to observe it at all. And lastly, but there's a third point is that if we already get everything we want from the spectra, and we want to move on to see new stars. So to conclude, time is the most expensive factors in spectroscopy, and we need a rapid feedback loop to decide early on which star is worth continuing observation. So let's bring, because that's a very challenging problem, and with traditional method, we cannot quite solve it. So let's bring in the AI guy. And the modern machine learning is becoming increasingly important in science. We collect increasingly larger amounts of experimental data, but our ability to analyze this data has not kept up with the data avalanche. Machine learning, in particular, variants of deep learning are emerging as a promising way to overcome this barrier. So can we develop deep learning algorithms that optimize the target selection, especially can they process raw noisy spectra and do it better and faster? So recall that the traditional spectral analysis takes several hours. If we can train a neural net to estimate parameters from the spectra and train it to be stable under extreme noise, then we only need a couple minutes of exposure time. And once the neural net is trained, it takes milliseconds to infer. So the lower bound of the exposure time, the lower bound of the exposure time is the accuracy of the neural net. Is that accuracy of the neural net must be high enough for the screening process. Therefore, we can form a rapid feedback loop. So there goes this amazing idea, the AI telescope, a telescope in a feedback system powered by AI tools. Just like the self-driving car, algorithms will be making decisions to select stars for us. As you can see, there are two loops in the algorithm. The shorter loop is the rapid feedback loop, and the longer one, the rapid feedback loop we just talked about, and the longer one with a period of months is the adaptive feedback loop, which refined the selection algorithm for the rapid analysis. It will be implemented with reinforcement learning. We need that longer loop because the science case of the survey are complex and multi-pronged. The problems are more complicated by not knowing what data will shown in advance. So we must be able to refine our target selection algorithm to adapt any changes, and we want to update it in real time. So in science, we also need to understand that I have talked about our AI solution to our problem, but there is problems with the AI. So we need, if we are doing science, we need to understand and estimate the statistical significance of our derived results. And there is a general skepticism towards the black box techniques. So for data with large dimensions, the networks can get quite large, making training slow and cumbersome. As a result, serious attention is being given to the physics-informed machine learning, how we can use prior knowledge about underlying symmetries, geometric, and physical properties of the data to simplify network designs. Here are the results of the dense neural net trained on the metallicity. From the top row is the effective temperature, metallicity, then the surface gravity. We can see that the results is not that ideal for the surface gravity because it's very hard to, the information is very hard to extract from the entire spectra. That's why we want to find some ways to do better feature engineering. One of the important properties of the spectra is sparsity. Most of the pixels are noise, and only a few informative pixels lives in a union of subspaces. And therefore, engineering informative features can be very tricky. So currently, we are exploring several approaches to rank the pixels by their importance in parameter inference. That is to measure how sensitive one pixel is to the parameter changes. For example, the red shaded region, there is like 3 distinct lines. It's called the Gaussian triplet. And these 3 lines only appear in stars that has lower temperature, which is the red stars. If you have a blue star, you don't have these features. So these are the key informative features, and the scientists over the years have derived a list of the key line features called the Lick indices. But the list is short and not complete. The question is, how do we do feature engineering? One way is to analyze each pixel at a time, or each line at a time, but it is time consuming and computational intensive. On the other hand, we can analyze the entire spectrum altogether. But as I showed you the results before, the accuracy drops because the information are being washed away as lots of pixels carry mostly noise. Therefore, we need to find the sweet spots in between the 2 extremes. We want an algorithm that can first group the pixels that change together along the parameter space, and second, drop the pixels that carry mostly noise. And third, we wanted to do it automatically. And the algorithm that can do such magic is PCA, the Principal Component Analysis, which is a dimensional reduction tool. Let's see an example of principal component analysis performed on stars in the blue horizontal branch. So they are the very blue stars, and you will not see the 3 lines I talked about before. The data we use is the normalized Bose stellar models. Notice that the PCA is done on the log of flux, because since the log of the absorption lines are additive. So in the bottom panel shows the top 5 eigenspectrum or principal components of the stars. The first one clearly shows the Poisson series, which will tell us the effective temperature. And the second and third combined will tell us the log G, the surface gravity. And the fourth and the fifth, you can see the spikes in there. They are the metal lines.
Excuse me, sorry. We have a technical problem.
Iska, can you hear us?
Yes.
Yeah, so we have a technical problem. The Windows has been rebooted, so
Okay.
give me a few 1 minute, something like that, and then
take your time.
You're getting back. So the last sentence was something like that when you started to explain the normalization of the spectra.
Is the Windows back? Or?
Kávészünetben most gépet cserélünk. Megy, az megy.
So, okay, let's just.
Ki van?
Okay. Iska, can you hear us?
Yes, yes.
Oh, okay. You are here now. Try to share again, please.
Okay. Can you see the slides?
Not yet.
Not yet.
We can see you. Now it's yeah.
Now
Is the slides up?
Okay. Oh no, go back. This was where we lost you. No, the next one.
This one?
On this, yeah.
Okay, so this is an example of PCA performed on the stars, like the blue stars. So the data we use are the normalized Bose-Stella models. Notice that the PCA is done on log of the flux, since the log of absorption lines are adaptive. So you can see basically the first PCs will tell us the effective temperature, and the second and third PC combined will tell us the surface gravity, and the fourth and the fifth eigenspectrum, you can see those spikes. These are the metal lines. So it can tell us the metallicity or the carbon percentage of the stars. Just to be clear, the figure shows the top 5 eigenspectrum or principal components of the stars. And an even better technique is called the principal component pursuit, or PCP. PCP is a method that makes the widely used statistical procedure principal component analysis more robust. It can decompose the data matrix into a low rank and a sparse matrix. It is widely used in computer science to separate the low rank background from the object of interest. For example, galaxy spectra can be viewed as composing of a slowly varying continuum and absorption lines, plus some sparse part of emission lines. We see that PCP does much better at extracting the sparse features than PCA. And there are some other projects we are working on, but I don't have time today to tell you guys. For example, we are building a generic model for the stellar spectra, which is the spectrum generator. And we are also building variational encoders on those intelligently engineered features, and also denoising autoencoders to get rid of the noise. We also apply these to aid the Bayesian hierarchical modeling, which Laszlo just talked about, for the actual target selection. We're also developing the reinforcement learning feedback loop for dynamically changing the target selection. So to conclude, my research is geared towards designing tools for the next generation AI telescope powered by deep learning techniques, augmented with insights from astrophysics, computer science, and artificial intelligence. Our work represents a recently emerging direction in AI, which instead of controlling self-driving cars, the AI is helping us to run our scientific instruments more optimally. With such powerful tool, we hope to tackle hard science problems. Yeah, thank you.
Thank you, Lisa. Sorry for this technical thing. So maybe we can have some questions from the audience, if anybody has. Related, you said somewhere that you are doing the normalization before application of the AI, and what do you do with the noise in that sense? So you normalize together with the noise, or you try to remove the noise somehow?
No. This is just because PCA will will pick up the nonlinear features, and so if we apply PCA on on non-normalized spectrum, it will pick up the overall shape instead of picking up those lines. So this is just an example to show you that what are these line features in the spectrum. That's why we use the normalized models. But for all the other applications, we use the non-normalized spectrum directly.
Yeah. Okay. Yeah. Anybody else for the questions? I cannot see any raised hands, so thank you very much. Problem, and I hope maybe you can continue with us. So thank you very much, and let's thank again Visca. Let's see the next speaker. The next speaker is Tony, I think. Yes, yeah. And Donny will speak about accelerating the solution of large number of delay differential equations with GPUs. That's 15 minutes.
Good afternoon, everyone. I am Daniel Knight from. Yes, it will be easier like that. And yeah, okay. And I am a student there, and I am also the part of the Sonochemist research group at the Department of Hydrodynamic Systems. And Dr. Ferenc Hegedűs is the leader of this research group and also the co-author of this work. And today, I'm going to talk about the acceleration of the solution of a large number of differential equations using GPUs. First, I would like to start with something interesting. By that, I mean some applications of delay differential equations. In that case, the recovery time of a disease and the incubation time of a disease can be included in the differential equations as a delay. A practical example is that would be the forecasting of the spread of a virus. A very different application is in the computer control of systems. Producing the output of a digital controller can require a lot of computational time, And this computational time can affect the dynamic behavior of the system because it causes a delay. Help us to avoid this kind of stability loss. A very similar application is in human balancing. But the main motivation of my work is the potential application in sonochemistry. The goal of sonochemistry is to increase the yield of chemical processes with ultrasound. Here, the wave propagation velocity is finite. And in very simple models, we model it as a delay between objects. All those equations that, yeah, so they are all low order equations. For example, in epidemic models, they usually use third order differential equations. In sonochemistry, we use second order differential equations. And usually those equations have several parameters. And sometimes we are not sure about those parameters, which means that, or we want to optimize those parameters, which usually means we have to solve a lot of the same differential equations. And we apply GPUs for that to accelerate the solution of a large number of differential equations. So the derivative xstat does not only depend on the state x, but also it depends on previous states. And this form actually describes a system of equations with m variables. And the x is the vector of the dependent variables, and those taus are the delays. And depending on the application, we bind. And the peculiarity of those differential equations that instead of initial conditions, we have to specify a whole initial function because of the delays. We must know the past. And in theory, those delays can depend on the state of the system, but in practice, those kind of equations are extremely rare. And from the implementation point of view, it's much easier to assume that those delays are constant, and it's also true in most cases. So in my presentation, I'm only discussing math. So to solve a delay differential equation efficiently, we should choose a Runge-Kutta method. And if we choose a p-order Runge-Kutta method, then a p-1 order interpolation method must be used so that we won't lose the order of convergence. And also because of the delay, we must know the past values. And for that, it's not enough to save every value. We must interpolate between those values. And for that, we should choose an interpolation method which doesn't the endpoints of the steps and the derivatives in those points. And the other option is using a continuous extension of Runge-Kutta method, which basically reuses the stages of the Runge-Kutta method to produce an interpolation. So for an efficient, so solving delay differential equations on GPUs requires some extra care compared to solving ordinary differential equations. But it makes sense to try the efficient ODE methods. It was found by us earlier that the pair-thread approach for ODEs is very efficient. We could reach in that publication 80% block efficiency. This means that this pair-thread approach has different parameters, and that's the only difference between the threads, that they solve ODE with different parameters. And of course, each thread uses the Runge-Kutta method, and they have the same fixed time step. From the implementation point of view, and there is also no communication between the threads. This makes the code both very easy to implement and fast. Well, the only problem with this approach is with branches. So for example, on if-else statements can cause thread divergence. But branches are necessary, for example, in the case of an adaptive solver, or if you want to do event handling. Our thread approach, which is using the GPU for vector and matrix operations, and basically solving a large system of equations and carrying out the necessary vector and matrix operations on the GPU. Well, it's all nice so far, but these require interpolation, as I said earlier. And this means two things. First, data must be written to the global memory after each step, because the actual state global memory before each step to calculate the necessary values using the interpolation. But if we want to save everything, that requires the allocation of a lot of global memory. Let's say we want to solve 10,000 first-order DDs, and each with 10,000 time steps. While allocating memory for that would require 1.5 GB global memory.
You mean global memory on the GPU?
Yes, on the GPU, yes. On even longer time domains. So usually the global memory is not enough. Our solution to this problem was implementing a circular memory pattern, because we have finite delays and we can actually predict that how much memory we need to have all the necessary data in the memory. So we are implemented a fixed size circular memory, which means that if we overwrite the values which we won't need anymore. GPUs. I implemented it in the ambiguous package, which is developed on our department. And originally it was for the for delay differential equations. And this is a general purpose delay differential equation solver for GPUs, which means that an arbitrary number of dependent variables or arbitrary number of constant delays and parameters can be specified. And I implemented it using Qt.C++ for GPUs. And I used the traditional fourth order explicit Runge-Kutta method. And for that, I used the third order Hermite interpolation to calculate the past values up to a third order precision. Okay, and the main steps of my algorithm is seen here. The first step is the initialization on the CPU. Then the blocks inside the red rectangle are run on the GPU. So the initialization consists of the setup of the time domain and the time step, and the delays and the initial functions are also set up here. Then the global memory is filled up on the GPU. It is important that we only need dense output to the variables, which has a delay. And by the dense output, I mean that if a variable has a dense output, then we can calculate this variable's value at any previous time step up to a third order precision. And here this circular memory is initialized using the initial function. And for that, the initial function must be discretized. And by discretizing the initial function, we get a nice and homogeneous code, and we can, as we use later. And then the iteration starts. And in each iteration, this time step is calculated. Well, this time step is a constant, but later, if we want to implement event handling or an adaptive solver, this might change. But those are not implemented yet, but later they might be. And the next step is calling the stepper function. And this is basically just the implementation of the explicit fourth order Runge-Kutta method. So we calculate the 4 stages with green, and we must read the past values here in those red blocks. Those are basically called a calculate past values function, and this actually does the interpolation of the memory read. Because we must use this time step later to calculate previous values. So has a dense output so that we can save some memory usage. And also at the end of the time step, a user-defined function is called, and this user-defined function can do easy things like finding a minimum or a maximum during the process. And the whole memory was implemented so that the memory access is aligned and coalesced. So it will be useful. So it will be efficient on the GPU. And then at the end of the time step, we check if the Next, I tested the performance of my code. And to test the performance of our general solver, this Ampigos, I compared it to several different solvers. Codes, and those problem-specific codes harness the maximal possible performance that we could reach, but they are not general. So basically, and I also tested one commercial solver for CPU. This is in the Julia language, it's the differential equations package. And for the tests, I used an NVIDIA GTX Titan Black GPU with 1.8 teraflops theoretical performance. And for the CPU, I just used my own laptop. But what is important that its performance is roughly 1/50 of the GPU. And to compare them, each code should carry out the same task so that they can be compared. For that, I created two test problems. First is the delay logistic equation. This is a very simple first order delay differential equation with one single delay here. And this also has a parameter. And basically the task is to run this delay logistic equation with different number of p parameters, and np denotes the number of different parameters we have. And for each parameter, I do 10,000 time steps. And I test problem for the delayed Lorentz equation. The only difference that it is a third order equation. The exact form is not really interesting now. Okay, so the runtime of the logistic equation is plotted here versus the number of parameters. As we should expect, the fastest code is the specific GPU code here with red. Around and the CPU and the specific CPU code is of course faster than this commercial solver for CPUs. And what is interesting here that for a low number of parameters, by that I mean around a few thousand, the change in the number of parameters doesn't really affect the runtime on the GPUs. That's because here we don't reach the ideal occupancy of the GPU. And I also profiled my code using the NVProf profiler in the case where I ran the simulation. For the specific GPU codes, the fastest configuration was to call the kernel 32 times and each with about 8,000 steps. For them, because it was a little different. And we can see that the memory implementation is very efficient, but we can also see that the Ampigos is much slower than the specific GPU code. All details, but then the flop efficiency of this is quite low. I did a similar test for the Lorentz equation. Here we can also see that the 5 or 6 times slower is the Amphigus, which is the general solver. And here I would like to mention that it only works to use GPUs for the solution of low order or differential equations or delayed differential equations if the number of equations to solve is very large. So here we can see that the runtime is still quite low, but if we would solve like 100 or 1 billion delayed differential equations, then this 5 or 6 times difference would be actually very meaningful. And I provide the codes again. Here I reached a better. Basically, we don't need to use that much memory operations for the interpolation, and there are more arithmetic operations in the system. To summarize everything, to summarize the test, we have seen that the specific GPU codes are run 30 times faster than the CPU solvers, and the difference in the capacity of the CPU and the GPU is around 50 times. And Amphigus was much faster than the fastest commercial CPU solver, of course, but Amphigus is not the ideal yet. The flop efficiency and the speed could be increased. And of course, larger system has better performance because it requires more arithmetic operations. In the future, I plan to improve the performance and add adaptive and add event handling in the solver. And also, I would like to try to implement adaptive methods. Well, the problem with adaptive methods is that the paired approach doesn't work. There it works to try a heterogeneous CPU-GPU solver, but I wouldn't like to talk much more about this. So in my presentation, I talked about what mathematical tools we need for an efficient solution for delayed differential equations. I presented my own algorithm. Then I implemented my algorithm in a general server and also for problem-specific cases, and I compared the runtimes, and I also measured the metrics of my codes I used, and also the solvers are available on GitHub.
Thank you very much. Questions? Please.
So is the only key difference between the generic and the specific GPU solver the memory layout, or there's more in the background that goes to
Yes, so for the specific solver, I didn't implement the circular memory because those were kind of small problems and we didn't need that. And that might be a large difference. Yeah, that's one. And of course, for the general solvers, we have the general solvers for any number of dependent variables, and in the specific solver, it was hard-coded that the number of dependent variables is 1. So it gives the compiler more option to optimize the code.
Congratulations, very nice work. I will just make a Can you give some examples?
Yeah. Sonocchiometry is not used in the industry yet. It's a plan for the future to basically it allows us to create some materials more efficiently than with regular chemical processes, just with the use of ultrasound. And this works because in a fluid there are several small bubbles, and those bubbles oscillate, and those bubble oscillations can thousands of Kelvin, and this can induce chemical reactions. That's the point. And it works in the laboratory, but it doesn't work in practice yet, or it's not used in practice yet. And those bubbles are modeled with ordinary differential equations, but there are like millions of bubbles. And those bubbles, of course, if about the yield of a process, we should simulate it, of course, and this requires the solution of a large system of delayed differential equations, for example.
One more thing. When you compare the specific CPU and GPU, what was the memory for the certain cases?
The memory?
The memory of the system. So was it the same or?
It's the same, yes, I run them on the same system.
But when you use the specific, see, I'll go to the maybe this one. No,
This one.
one.
Oh. Specific CPU and the GPU.
Yeah. Sorry, maybe this
Yes,
way is
yes,
better to
okay.
understand.
So for the specific CPU code, I just run it on one thread on the CPU. Yes.
Okay.
So of course it has, so it's much more efficient, of course, because the CPU has better functional logic and everything on the CPU. Because for example, for the GPU codes, we need like 80 or 100 registers per thread. So there is some registers fill also. And in CPU, it's not a problem because we are solving one equation. So.
Oh, okay. It's very nice. And congratulations on this night. Thank you very much again. As before the break, Toshi, mixed precision when is it versed?
So hello everyone. Yeah. Hello everyone. I'm Vani Chikros, a PhD student at Pazan Péter Catholic University. In the next few minutes, I would like to work around a little bit about mixed precision computing. First of all, I will try to define what is mixed precision computing with some additional notes that why it is really a useful tool, why is it a hot topic today. Then I will give you some examples for this domain. So most of the scientific applications are using the IEEE 754 representation for floating point numbers. This gives us several different sizes. The 64-bit wide double precision, 32-bit wide single, 16-bit wide half precision. All of them are coming with their own parameters, different dynamic ranges and their own precisions. If we have an application defined in double precision, but we change everything to single precision, it is really clear to see that that we will have and so on, but our final result might be invalid or a little bit wrong. So, thank you. So we have to think about that how much we can lower the precision of the algorithm. We have to find the perfect ratio. We cast one part of our application from higher precision to lower precision. But another problem here is that during the runtime, there might be a lot of conversion. That is another problem that we have to think about. Of course, there are some other representations which can help on this. For example, the TensorFlow 32 from NVIDIA and BFloat 16 from Google. Both of these representations have the same dynamic range like the FP32, but with smaller precision. So overall, we have smaller numbers in representation. These are much quicker. And they collected the most important challenges that we have to face if we want to get to the exascale computing. The first big challenge was the power consumption, and the technology at that time to have the 1 exascale system, it would consume 600 megawatts of power, which is not really acceptable. By today, we are under the 20 megawatts, which is pretty fine, but that was one of the main big problems. Second main problem is the speed and energy of the data movement. It took more time to move the data, move one piece of data than to execute the operations on it. So we have to work on that also. Third is the fault tolerance. If we have way more operations, failures can happen much faster, much more frequently. Checkpointing is still, it was still really slow. And the fourth one is the extreme parallelism. If we think about that, if we want to get to the which can handle 1 billion calculations every second. So these were the 4 main challenges. And from these 4, three of these can be communications. The data size is much smaller. The memory ball is much smaller with that. We use less memory in the, at all in the system. If our numbers are represented in smaller sizes, then the operations can go through quicker. We can have more flops per second, and so on. And also there are some specific we can have way better performance, for example, in FPGAs. If we halve the size of the numbers or the representation, then our performance speedup can be in the fourth. For example, or in NVIDIA GPUs, we have these tensor cores, which are really effective tools for that. Others already recognize these including 2 Gordon Bell Prize winners, best paper at IST 19. At the end, you can check the references at the end of my slide. They will be updated. To some examples. First one is just a really simple one. Let's imagine a Lagrangian particle method problem. We have particles somewhere. They have a position, which can be basically anything. And that is pretty important. Let's keep it in 64 bits wide representation. But the movement, the displacements, will be probably a really small number. We don't need the dynamic range. And this way, a part of the application can be can run quicker. Let's get to a real problem, which is already measured. In machine learning at NVIDIA, they created a mixed precision training method. What they do is that they store the weights, the activations, and the gradients in half precision. And in each iteration, and they keep a master copy of the weights in single precision. They calculate with the half precision ones, and in each iteration they do an update on can somewhat match the original half precisions, original single precision method. More details in their paper. Rule of thumb, the relative residual accuracy will be the production of the unit round-off, the smallest representable number in absolute value with one represent round-off and the linear systems condition number. If we apply them in a conjugate gradient solver in double precision, with double precision, the unit round-off will be 10 to the minus 16. So after a lot of iteration, we can get a 10 to the 12 accuracy improvement. If we do the same application in single precision, because of this rule of thumb, we will have about 10 to the cubed improvement, which might be not enough for our application. But what we can is that if they redefine the problem at each level, they can again win or 4 of accuracy. They redefine it again, and they received almost the same final accuracy. And the end with improvement with this method. Another example we can see at the GPU mixer. What they do here on a kernel level, they introduce these so-called fast imprecise presets. They put one operation into them, and they compute the dependencies from everything outside of the preset is in double precision or in higher precision, and inside of presets they cast everything to a smaller or a lower precision. So they calculate that how many data comes in, how many of this set, and they compute that how many operations, arithmetic operations, are inside the set itself. In this case, we have 3 casting operations and 1 multiplication, an arithmetic operation. We have a 1-to-3 ratio. And they modify the kernel itself when this ratio is bigger than 1, and they want to maximize it. So they extended, but the algorithm extends the set with the neighboring operations. Again, they calculated operations this way. In this case, we have the 2-to-3 ratio. And if we continue the algorithm at the end, we will have 4 operations inside arithmetic operations and only 3 casting operations. And this is bigger than 1. So we can conclude that in this kernel, we can, it works to cast this part into a lower precision. Yeah, and this way, some benchmark tests decision. Here is another input also, what they check from the user, that what precision they want at the end. They do some trial tests for each kernels and check whether the final result is still within the predefined error bound. What we realized here is that we can more mixed precision techniques if we know more about the application itself from the further view. to do then, we can use some domain-specific abstractions. Through these, we can receive some further knowledge about the applications. The idea here is high performance computing, for example, or not efficiently, then he can declare the problem that he wants to compute, and without specifying the exact implementation, so just the physics, and he can use some. From that, we can which can target different hardware or software platforms also. And from these domain-specific constructs, we can exploit some further knowledge as well. Such a system is the OP2 domain-specific library, which is developed for computational fluid dynamic codes and distributed memory clusters. It separates the high-level description from the parallel implementation. It looks like a conventional library, but it uses code transformation. Here we can see an example. If the user can define firstly the kernel function, and it is defined on an edge. And then later the user calls an OP for loop function call, and here he defines that on what elements he want to run the application. This one. So it defines the kernel itself, some name, and we have a set of elements where the user wants. And then we list, or then the user lists some other arguments about how can he reach the data, or how can we reach the data. And on this point, we might find this further knowledge, or we can also read the kernel function. If we realize that if there is a function, for example, which increments one variable each time, and it is zeroed out, then we might say that if we move it to a lower precision at one point, then we will not really modify the. This we can generate mixed precisions. We tried this example just on one simple CSV application called Airfoil, where we just, for the first view, realized that, okay, if because it is just incrementing one variable each time, then the output will be valid. And with that, we already achieved a 10% speed up easily on an Intel and then on an NVIDIA stations as well. This research. There is still a lot of room where we can go with this speed up. In theory, we can get to this part at the end. But the question is that how can we automatize it and on our systems or on our applications. So I am open for questions, although there is a big chance that I cannot answer them because we are still at the really beginning. comment or some additional thoughts that what should we think about, what should we
data into cells, into sets, so you lower the precision, the process is faster. How do you recover so you know that the data at the end will have the required precision that you want? Like I don't know, like I know that it is separated in sets, so it lowers the precision, you can calculate it faster, but how do you have the last result so you know that it has the precision that you want?
There is one thing that they've done in the GPU mixer application or in method that they've done these trial runs. For each kernel, they tried it first, whether it will be we might do it this way. Not sure yet.
Okay,
but
I think that in the going to this kind of big environmental models can be something in which you can focus. Like for example, the one that you presented at the beginning, like climate change, have a lot of data that can be like partitioned to apply this kind of things. Like I think for the first one, that if the climate change simulation that should have problems with image rendering or the
okay, thank you.
Further questions? Please.
Done again at this GPU mixer. They try to get from the papers from the Harvard descriptions, and they couldn't find any details about it. And they measured it that this is a good idea to think that one arithmetic operation is equal to one casting operation.
On CPUs, this information is available, not really on GPUs.
Yeah, so this work was only on GPUs. On CPUs, we didn't try to.
So would that be that one arithmetic is the same as cast? Would that be true for all kinds of arithmetic operations? For example, divisions? I think they are more expensive. Yeah, so.
Yeah, we didn't test it yet.
Okay.
So yeah, good idea to check on that also.
Okay. If there's nothing left, it's time for coffee, and let's thank Gary for his presentation. Adam Padlecik and Károly Kubicko is here. Yeah, so please, if talks, upload the talks.
Akkor gyorsan adjuk, mert nekem meg lassan gyorsan mennem kell. Hát jól lerögzítettem, azt hát
Annak a mikrofonja kapcsolódik.
A mikrofonja ki van?
Micsoda pendrive-od van?
Nem az enyém.
A tiéd?
Na most a helyzet a következő. Én nekem nagyon sürgősen fel kell menni. Itt hagyom a gépet. Ez most rá van dugva a kamera. Működik a kamera. Van. A hang az ott van, tehát ugyanúgy tud továbbra is beszélni, az lesz továbbra is a prezentálója. Hát a kettőt kell valahogy összehozni. Jó? Rohannom kell.
Rendben.
Are we online? Okay, so the last part of today, let me close this. Afternoon's traffic starts. So the next speaker is Adam Kadlecik, and we'll speak about something happened. And we'll speak about the laboratory observation of water surface polygon. What is this? This is just start with a nice blue something. Thank you, Bill. It was a nice thing. I think it was pretty good. So, Chap 13. Chap. 13? De nem azt mondtad? De. Igen? Oké.
Mindjárt újraindulnak.
Minden újraindul?
Az előbb úgy történt.
Very nice. This is a kind of, adult protect not to spend too much time.
This is a feature.
A feature, yes. It's a healthy Windows edition.
Sorry, the blood pressure.
Ez volt.
Okay, so action 2. Adam, please.
Greetings, everyone. Okay, thank you. Greetings, everyone. My name is Adam Kadlecik, and I'm not really going to talk about GPUs today, but rather of a phenomenon that we can observe from a laboratory, and I talk about some simulations about it. So, but to do that, I need to show you the phenomenon itself to understand it. So, okay, so first I'm going to give you an introduction of this phenomenon. Then I'm going to show you how we reproduced it. I give a qualitative explanation of why it exists. Then, if I have the time, I talk about the measurements we did. And after that, I show you actually the quantitative theory and the simulations and all that kind of stuff. So, as an introduction, first I'm going to show you a phenomenon that's quite similar to the one that we were observing. I'm sure many of you have heard about Newton's bucket, which is basically a bucket filled with water, and it is rotated around its axis. And because of centrifugal force, the water is pushed outwards, takes up a paraboloid shape, and yeah, that's basically it. It's quite an easy thing. Even Newton himself has tried it out. Now, what we do is different from this in only one way, which is that we do not rotate the whole bucket, only a plate near the bottom. So that means that we only rotate the bucket's bottom, the balls remain stationary. And from this, what we get is that while in the middle, the liquid will want to move with the rotating bottom plate, near the walls, it will want to stay stationary, and it's going to gain this quite weird shape. And of course, again, if you rotate it the high enough frequency, then in the middle, the water will be pushed outwards completely, and it will have a dry middle. Later, we'll see why this is important. So what really is the difference between these two things, the Newton's bucket and our phenomenon, is this boundary layer that we see there, which I'm going to call delta. This is going to cause of very of a lot of interesting things. But let's see how this delta actually looks like. So here are the two buckets. They are rotating, and we have the liquid inside. And we're going to look at this part of the liquid, namely its tangential velocity. And what we see in the Newton's bucket case, that of course, as we go outwards, its velocity is going to increase linearly. While in our case, in the middle is going to go similarly, but near the walls, it's going to drop down quickly. It's going to have a velocity difference. If we plot this on a qualitative graph from the laboratory frame, we see that near the middle, we see some kind of a solid body rotation, but near the wall at this delta boundary layer, we see a velocity shear. It's even more interesting if we look at it from a co-rotating frame, where again, at this delta, we see a faster flow velocity shear. And this velocity shear is going to be the reason that we see different and more complex shapes. Well,
so would it mean that if you would have a superfluid, then it would be the same?
Well, I'm not sure about that.
Then you cannot get it to turn up.
Yeah, okay.
So, but I didn't really show you any shapes yet, so I'm going to go ahead and do that. So I show you how we make this phenomenon. Here's a sketch about our measurement setup with the bottom plate, the cylinder, and the camera from up top. Here's the actual setup we use. We have a motor, transmissions to highest frequency output. We use cylinders for the bucket, and there's the rotating plate. And here is a video of the phenomenon we made, which is a bit, I don't like PowerPoint, but I think the main thing can be seen that the camera is looking at it from the top, and we see a rotating square. Now you might ask if we can only make squares or not, and no, we actually could achieve circles, ellipses with two corners, triangles, and squares. In papers, you can read about pentagons and hexagons as well. I haven't read about a septagon so far, but I think that's plausible as well.
Excuse me, what is the number here?
N is the number of corners of these polygons. Yeah, so I talked about that these polygons exist because of this delta boundary layer, but I didn't exactly tell you how. So what we see here is a hydrodynamic instability. If you're not familiar with that, it is an example for that would be Kelvin-Helmholtz instability, which is when we have two different fluids with a relative velocity difference as seen on the simulation. And what happens is that these wave-like shapes start forming. Actually, you can sometimes see this phenomenon with clouds. There are really nice pictures on the internet of this. And now in our case, we do not have different fluids, only a relative velocity difference with this delta layer, but that is enough for us. So what happens here is that we have this velocity shear in the fluid, and let's say that small perturbations form spontaneously. And what happens is that I show this on this sketch, that we have here a flow, and because of the small perturbation, its cross-section decreases. And because of continuity, its velocity will increase, but on the other side, the velocity will decrease. And Bernoulli said that when something, a flow is faster, then its pressure is going to be lower. On the other side, it's going to be higher. So this perturbation will grow. And these will be these wave-like shapes that we see later. Okay, we have waves. How do we have polygons from those? Now, in these polygon vortices, we have these waves basically, but do not forget that we have a periodic boundary conditions. These waves basically go in circles. So what happens is that only those wavelengths are amplified, which fits on this circle round number times, integer times. And this is exactly what we see here, a sketch of that we have these waves that fit on this circle, and these are the polygons that we see. Another way to phrase this is that these waves interfere with themselves, and we see their superposition. So this is the reason that we see these polygon vortices. Yes, so during our measurements, we made measurements on what kind of parameters, how affect these polygons. by that I mean with different initial conditions, what kind of corner numbers we got. And I think I have a bit of time to talk about this. So we made a few phase diagrams of different initial conditions, like different radii of the bucket, frequencies, and height of the liquid. And yes, we can draw some conclusions from this. What I really want to say is that these experiments are quite reproducible. So if you give the same initial conditions today and tomorrow, you get the same polygon. Okay, so now on to the quantitative theory. The equation of motion would be, of course, Navier-Stokes, which writes down fluid dynamics. We really can't wait for an analytic solution because this is, of course, a turbulent flow. And the only way to really solve this would be to make a numerical simulation. And during our research, we really didn't have any experience with doing this kind of simulation. So we asked around what we should do. And we were told that we should try a program called OpenFOAM. And we got a computation time at the GPU level of Wigner Research Center of Physics. And what we did is made a few simulations. Here are those, and the last one is really just a pilot simulation to try the program. But on the right side, we have a simulation which was meant to, which are at initial conditions at which we should be seeing a polygon vortex, but we do not. And that is mainly because probably the mesh wasn't fine enough to actually see this, because in this kind of phenomenon, as I told earlier, small perturbations need to grow, and small perturbations cause the whole phenomenon. And if the mesh is not fine enough, we do not see these small perturbations growing. So what we would need to do is even make the mesh even more detailed. But even the above-mentioned simulation took days to calculate. So what we really see is that these numerical simulations are quite complex. They are hard to calculate. And because these small perturbations need to grow, if these small perturbations can't start because the mesh is not fine enough, we won't see the simulation properly represent this phenomenon. So what we later rather do is that we didn't run simulations, but we actually did the experiment itself, because it made a little bit more sense to actually do that than running simulations in this case. And what we wanted to do with our theory actually is to take a step back and look at this whole phenomenon from another angle and see if these polygons are actually similar to something else which can be written down with easier equations. And what we said that what if we sit into this bucket and we are in a co-rotating frame, and what we experience is that we have a gravitational acceleration and a centrifugal one. And from these two accelerations, we can get a new effective G prime. And what if these polygon vortices are none other than water surface waves on a tilted surface with this effective acceleration? Now, to prove this, what we need to do is take the water surface wave dispersion relation. Water surface waves are waves that can exist, for example, in a pond or a bathtub. And this equation gives a correlation between the frequency of the wavelength, the gravitational acceleration, and the water depth. And what we did was that we modified this and tried it out for our polygon vortices. Here is the modified version, where we have the frequency of the wave in the co-rotating frame, which is quite interesting that these polygons do not rotate with the same frequency as the plate near the bottom is rotated. Here you have the above-mentioned effective G, the wavelength of the polygons at R mean, and yeah, what is the water depth? Well, we can't really say, because if we imagine which water depth should we be looking at, so what we do is give an order of an estimate for the order of magnitude as so. And what we did is we plotted the measured frequencies with the calculated frequencies and see how they line up. And we see that this is how they line up around a fitted line, which is slope is around 0.42. And from this, I would say that we can see that these polygon vortices can reasonably reasonably looked at as these water surface waves on this tilted surface. Now I would like to summarize. So yeah, I talked about polygon vortices, and they're caused by shear instability. And from our research, we get that these are quite similar to water surface waves on this tilted surface. Now here's a picture of Saturn's North Pole, where I'm sure many of you heard that there's a hexagon. And if I know correctly, that is a quite similar phenomenon to this. That is caused by shear instability as well. I would like to ask, thank you for your attention.
Thank you very much. Any questions?
You mentioned this description with the co-rotating frame, but you also mentioned that each radius rotates with a different speed. So,
we took the mean of it. Well, basically, what we looked at is that we have this delta shear, that's delta boundary, and at the end of that, there is really the difference between the two velocities, and that was the position that we looked at, where we looked at this X velocity.
Further question? Is there any continuation of this work with us?
We don't know yet.
Okay.
Maybe.
Right. So. Okay. If there's no further remarks or comments, let's thanks Adam again. Carol is not here, yeah? Yeah, come on, guys. Sorry. So Karol Kubiczko will speak about hydrolysis of and dimethyl. Oh, I cannot make today is too late. It's your duty. Please, but we need to talk in a memory stick. Can we make that like?
Yes. I have a memory.
Or shall we make something? Meg tudjuk csinálni? Nem úgy, a sorrendet nem, a laptopot. Ja. Megvan?
Nem ez az? Indikon fent van, nem ez az?
Ez az asztral.
Ja. Akkor nem. Ja.
Van USB-t? Okay.
Pendrive-nak hívják az eszközt. Formázni szeretnék.
Itt be tudod tudni, ott nem formázom. Slides. Ha itt lesz, akkor az Próbálj onnan direktben a csorrendszert. Okay, so now you will see why I do not want to try to read the title of the talk, but but Caro is a long time ago a user of the GPU laboratory, so please.
I welcome the audience. My name is Károly Kubicsko from Eötvös Loránd University. In my lecture, I will speak about the hydrolysis of NN dimethylindole 3-ethaniminium cation, the oxidized form of the endogenous psychedelic NN dimethyltryptamine.
Okay.
First, I would like to briefly summarize what will be discussed in the lecture. I will speak about the applied methods and present the chemical reaction of interest. For this followed by the discussion and summary of our findings. Within the framework of Born-Oppenheimer approximation, the motion of electrons and nuclei can be separated. The electronic and nuclear Schrödinger equations can be solved independently. In our work, we focus on equation 2, the electronic Schrödinger equation. All computations were performed using the Gaussian C1 program package. The examined systems contains 31 to 37 atoms. At first, we wanted to use ab initio methods, but we found them extremely time-consuming. Therefore, the DFT approach was our choice to be accurate and computationally affordable. The M0 to M062X OCC DZ level was used for geometry optimizations and frequency calculations, as well as the thermochemical analysis. The M062X OCC DQZ level has been applied for single point energy calculations. The best available integration grid was chosen in all calculations in order to take account of the solvent effects. We used the assembly variation of IEFPCM so implicit solvent method.
Maybe the mouse is not over the. No, it should go. No. Yeah. Try to move now. Oh, it's
Okay, okay. Okay. The the total gypsy energies were computed as shown in equation 4. The gypsy energy corrections determined at 36 centigrade and atmospheric pressure in order to simulate the environment of the body. The activation barriers and the reaction rate constants are connected. The connection between them is described by the equation 5. Knowing the activation barriers, the corresponding reaction rate constant can be calculated. The lowest rate constant corresponding the highest activation barrier, which is the rate determining step of the reaction. Okay, so on this figure, in this figure, the metabolism processes of 3 biogenic amines are presented. In the first row, the tryptamine, the second row, and the N-methyltryptamine, and the third row is the N-dimethyltryptamine. The first step of the metabolism process is the oxidation by monoamine oxidase. During the enzymatic reaction, the FAD cofactor of MAO is reduced to ZH- and the amines oxidize to iminium cations. It is followed by the hydrolysis of the iminium cations, which results in indole 3 acetaldehyde and the corresponding amine. The final step is the oxidation of the aldehyde by the aldehyde oxidase or the aldehyde dehydrogenase enzymes, and the product is the indole 3 acetic acid, as known the auxin hormone, which is the main growth hormone in plants. I labeled the examined reaction by the red rectangle. This figure, the schematic figure shows the hydrolysis of a general iminium cation with hydroxidion. In our case, the R group corresponds to methylindole group, and Q and Q prime are methyl groups. The first step is the addition of hydroxide anion to the immunocarbon. This step is followed by an intramolecular proton transfer from the oxygen to nitrogen. The last step is the cleavage of the C-N bond, and therefore aldehyde and secondary amines are produced. The examined reaction contains the EMDMP plus cation and one hydroxidion with 0, 1, and 2 additional water molecules, as can be seen on the figures. The whole reaction contains 4 elementary reaction steps. The first is the addition of hydroxidion on the carbon atom. It is followed by the inversion of nitrogen. This is necessary because after the addition of hydroxidion, the lone pair of the nitrogen and the hydrogen of the hydroxyl group is on the opposite they have opposite spatial orientation. Therefore, after the inversion of the lone pair, the possibility to form a hydrogen bond between them is possible. We found that the rate determining step of the reaction is a concerted proton transfer from the hydroxyl oxygen to the nitrogen. This figure shows that the effect of the additional water molecules, the highest TS3 activation, TS3 transition state corresponds to the determining step, and with 1 and 2 additional water, the height of this barrier can be reduced. On this figure, I presented the structure of the transition state in the R0 reaction with just the hydroxidion and the iminium cation. A 4-membered transition state, the 4-membered ring has in the transition state, and by applying 1 or 2 additional waters, this structure, this 4-member structure. It extend to 6-membered or 8-membered rings, and this geometrical this enables a geometric relaxation of the structures. So in our study, we found that the concerted proton transfer process is the rate determining step. By applying additional water molecules, the activation barrier significantly reduced with one water, and with applying another water, it can be reduced further. Thank you very much for your attention.
Thank you very much. Any questions?
I'm assuming you do your calculations with some kind of density function, right?
Yeah.
So do you use some available package like the VMA package or also the package, or do you have some own development?
We just used the Gaussian 16 program package in our work. This was the only software.
Please.
If are not like, okay, I will think about it. You are adding 1 or 2 additional waters to reduce the energy boundary between the transition states. It's just this geometrical structure that helps in the relaxation of the molecule, and it's not a bond, it's not a ionic bond, it's not a covalent bond. What are the interactions that are like, whether they are yeah, like there.
Yes. So the water molecules form a hydrogen bond between the hydroxyl group of the intermediate, and by this hydrogen bond, the proton can be transferred more easily. So
that was my question.
Okay, so can you repeat the question?
No, it was I wanted to know if it was like I don't know, van der Waals or like it was a nitrogen bond.
Hydrogen bond.
Okay, any further questions or remarks? If there's no, let's thank Farai again. Next speaker is Ákos Sudár from MINES, and he will speak about parallel proton city image reconstruction, which is part of the Bergen PCT collaboration that we are very much involved. Please.
All right, so welcome everyone. Today I will speak about the image reconstruction of proton city images, and I will show my work with the Barnaföldi Gergely Gábor Barnaföldi, Mónika Varga Kőfaragó, and Dávid Végrádi. So first of all, what is CT imaging? So during CT imaging, we take kind of 2-dimensional images about an object, and we do it from lots of directions. And finally, we want to reconstruct the 3-dimensional distribution of some material properties. And this material property, in case of proton imaging, is the relative stopping power of the material, which is the stopping power of the material divided by the stopping power of the water in the same proton energy. So why it is important for us? It's very important because it requires information for treatment planning to proton therapy, which is a novel treatment technique against cancer. And the use of techniques is increased, is more and more frequently nowadays. So the motivation to improve this technique is increasing as well. So the Bergen PCT collaboration was established to develop a proton CT detector, which is visible here. And it contains 2 tracker layers in here and 41 calorimeter layer. Each contains more than 100 silicon pixel sensors. So it's a quite huge and complex and expensive detector. Takes years of works of a whole group of people to develop. So, and the image reconstruction is an important step of the imaging, as it has a direct effect on the quality of the final image. And this effect is how to say, nothing detectable, so it's a significant effect. So, and compared with the development of the whole detector, it's the development of the image reconstruction techniques requires only some person. Of course, it also requires years, but doesn't really require other sources, only computational power. And that's why I talk about this here, because it requires a lot of computational power. So anyhow, let's try to find a proper image reconstruction technique, and it's worth to optimize it as to maximize the advantage comes from the development of the proton CT detector. So first of all, what's our problem? We have a patient which we would like to image, and we divide the patient into small volumes called volumetric voxels with an analogy of pixels in an image. And we can imagine the imaging process like the proton goes through these voxels and has an interaction with every voxel. And this interaction can be described by beta block equation and multiply Coulomb scattering and other effects as well. The whole imaging process can be modeled with a matrix multiplication, as it's visible here, where the A matrix contains the physics, which is these interactions, and X contains the relative stopping power of the voxels, and Y is the measured data, which is the energy loss of the protons. And some words about the size of this system. So our task is to solve this linear problem for X, and some words about the size of this problem is that the number of voxels can reach 10 to the 7, and the number of measured protons can reach 10 to the 9. So the system matrix itself is even huger. So we cannot use techniques like pseudo-inverse to solve this problem, as it would run forever. So another problem that the A matrix is very huge, and we have a fortune because it's sparser. So as each proton interacts with only a small subset of voxels, but even the non-zero elements of the matrix can reach 10 to the 12, which is as large as it's not so efficient to read it from a disk in every iteration of the solution. So we handle it as a function. So we calculate every coefficient when we have to use the coefficient, and recalculate if we would like to use again, which is a bit time consuming, but way faster than read terabytes of data in every iteration. So because we need a lot of computational power, we use GPUs and we use a multi-GPU system. And yes, we have a huge problem. So let's another main aspect of our image reconstruction technique that we don't want to read all the proton histories at the same time, as there is numerous proton histories, and we don't want to run out of memory, and we don't want to limiting our solution for an amount of protons. So we would like to be able to theoretically infinite number of protons. So, and this point will dominate the solution technique, the wheel of solution technique. And of course, we would like to have a well parallelized and well optimized solution. So some words about the solution algorithm, which is called Richardson-Lucy algorithm and comes from the field of astrophysics, where it was used to reconstruction of telescope images. And it is known as a fixed point iteration and successfully used for emission tomography. So I hope it will be efficient for proton CT reconstruction as well. And okay, so in the beginning of this solution, we have to say to give an initial guess for the image, which is practically a unit vector in my case. And here we have a formula to update the value of one voxel based on the previous approximation of the distribution. And I will speak about the application of this formula for parallel GPU image reconstruction. So first of all, here in the left-hand side, you can see the approximation of the relative stepping power of the voxel in the next iteration. And here in the right-hand side, the first element is the previous approximation. And this second element is a fraction, which is kind of a normalization fraction based on the whole interactions in which the voxel participate. So it can be calculated pre-calculated the iteration cycle itself, and it's accelerate the solution. So let's do this. Our second modification is based on the fact that we would like to evaluate our iteration from proton to proton. So instead of calculating this summation directly, so goes through this summation, we define a ratio vector which contains an element for each voxel and set it zero in the beginning of the iteration, and later read a proton and calculate this ratio for every voxel which has an interaction with the proton and add this value to the ratio vector of the voxel. And our third multiplication is about this ratio, because this ratio has a name called Hadamard ratio, and its physical meaning is that it is the energy loss of the proton divided by the approximated energy loss of the proton based on the approximation of the distribution the previous okay, so we can calculate this ratio for the proton and later just use it for update every element of the ratio, vector for every voxel which has an interaction with the proton. And here you can see the full algorithm. So first we calculate the normalization, and after we start the iteration and use as many iterations as needed for the image reconstruction, which is typically 20 to 300 iteration. And then we read a bunch of proton histories. And first we calculate the Hadamard ratio for every proton history. And we do this in a simple way that each thread of the GPU calculates one Hadamard ratio. And as a second step, we update the ratio vector of the voxels, but we do it with a different parallelism. Like we read the Hadamard ratio serially and update the ratio vector of voxels. So update parallelly the ratio vector itself. And why do we do this? Why don't go just through? Why don't we evaluate each proton histories parallelly here as well? And the reason is to avoid race conditioning, as a two proton can have the interaction with the same voxel, and if different triads would calculate the interaction of the voxel and the proton in the same time, then they could then it could have happens that two triad would like to update the same ratio, same element of the ratio vector as in the same time. But as one proton can interact once with voxel, this solution avoids this race conditioning. And yes, in the end, we update the image vector. And here I would like to say to show some results. It's a reconstruction of a de Renzo phantom. The de Renzo phantom is designed to measure the spatial resolution of an image or an imaging system, and it contains groups of rods with the same diameter distance from each other and in a triangular structure, and there are different diameter regions, and the evaluation of this phantom is quite complicated, but a simple method just look into the phantom and let's decide which group, in which group we can see the rods and in which group not. And here we can see the rods in 4 groups and cannot see in 2 groups, which is a reasonably good result. So yes, let's end my presentation. So I started a new development in the field of image reconstruction for proton CT, which is in development in the direction of the use of statistically based image reconstruction techniques for proton CT. And I applied the Richardson-Lucy algorithm, and I reached reasonably good spatial resolution and acceptable relative stepping power resolution with this algorithm. So I will continue this work and I will optimize the parameters and the performance of this algorithm. And later I plan to develop a new algorithm for proton image reconstruction, specially designed for proton image reconstruction based on maximum likelihood method. Thank you for your attention.
You told about the.
Maybe remove the. Okay, it's more.
I was talking about the non-zero numbers of the matrix, but how large is a regular image vector?
Regular image vector is between 10 to the 6 and 10 to the 7. But it really depends on the application. So it's true for proton imaging. Probably in nuclear medicine, it's usually smaller.
And the Y vector?
The Y vector is 10 to the 8, 10 to the 9 in case of proton imaging. So it's some 100 million proton history.
When you talk about tensor beam, is cone beam for imaging? It's the same.
No, it's not the same. So the passive beam means, so in case of how to say, in case of a commercial radio X-ray therapy, they use a big field for irradiating the tumor, kind of 10 centimeter times 10 centimeter or something like this. And in case of tensor beam, we use a proton beam with the diameter of 7 millimeter or something like this.
So you cannot use, for example, the Feldkamp algorithm that is normally used for the reconstruction of cranial images. Is like that.
Sorry, which algorithm?
The Feldkamp algorithm is what they use for the reconstruction of CT images for the cranial parts of the, like when you make an encephalogram. Like what is the difference between that one and the Lucy algorithm? I guess it's more optimized for smaller things, because you are for sure reconstructing images that are a little bit smaller.
So, do you mean theater back projection or what? Or
no, it's when you have this, you will have a lot of images in a zip format, for example, and then you make the reconstruction with this algorithm. That in your case you are using Lucia, right? I don't know if you know what is the limitation of the Feldkamp algorithm. That is the normal one that is used for reconstruction of CT images. Like
so
maybe you know.
by my knowledge, the regular CT images is reconstructed based on image reconstruction. So based on integral transformations and the reconstruction techniques based on integral transformations. And I use image reconstruction techniques based on statistical motivation. So based on this maximum likelihood theory. And these are really different kind of algorithms. And there is two main differences. The first, so how to say, I have more flexibility to implement how to say, not straight line pass of the protons into this algorithm. And the other is that this algorithm works better with low statistics compared with the integral transformation based algorithms.
So actually, one of the main problems with the proton imaging that the stopping of the proton is very nonlinear in the regime where you are doing the thing. So it's not just like in the standard X-ray, you have a almost linear losing loss of energy through the body, depends slightly with the, of course, proportional to the density. But here we have sometimes real stopping in the certain area. Okay, so it's highly nonlinear. So some of the methods cannot be used in an ordinary way. So what Akos did is this method is never used before in this way. So it's a fully, completely new thing developed by him. Further questions or remarks? There's nothing else, but let's thank Akos again. The next is Daniel. Sorry, not I missed the thing. Balázs Majos. Sorry. And it's also the standard topic from the GPU laboratory, the challenges and methods of tuning the Hygiene plus Monte Carlo event generator, which is for one of our big projects. Particle Monte Carlo event generator. So Balázs is one of the new member of the group doing this interesting stuff. So
yeah.
Please.
So hello everyone. I'm Balázs Majos. Thank you for the introduction. And so I've been working with Gergely Gábor Barnafeldi and Gábor Zero for around a year to tune the Hygiene plus Monte Carlo event generator. And it's not working, sorry. Okay, I'm going to do this right here. So first, let's tackle the question. So why Monte Carlo event generators are important. So it provides a detailed simulation of high energy collisions, and it's widely used by both theorists and the experimental community. And it's very useful for designing new experiments and to make predictions and to put our physical models to test. So I'm sure everyone has seen a picture like this. Like it's a proton-proton collision in one of the colliders. And you can see that it's a quite complicated event. And this is a reconstruction of a Monte Carlo event generated event, but it's reconstructed graphically. And so it is quite computationally expensive. As you can see on the next slide, I'm going to show you how, on the next slide, I'm going to introduce you to how some of the statistics, but let's go back once first. So Hygiene is a Monte Carlo event generator for proton-proton and heavy ion collisions. It's currently pre-release, so it's under development. And that's why it's so hard for us to tune this system. It's the successor of the old Hygiene, which was written in Fortran, and it's rewritten now in C++. And it has a native support now for CPU multithreading. And it's quite good for us because tuning would take eternity otherwise. So yeah, and you can see on the picture so how you can imagine a Monte Carlo event generator event. It's two nuclei collisions, and in the lower you can see a global model of the two nuclei collisions, and it's used to calculate several geometric quantities. And it's a very intricate system. It's very complex, and its output depends on several internal parameters. And we have to examine around 40 physical parameters, which are just the hydrogen plus parameters. And these are theoretically not calculatable. So we have to use almost a better brute force algorithms or tasks to determine these parameters. And for one system, it's really easy to calibrate an event generator. I mean, one system is like a fixed energy and a fixed system for example, a proton-proton collision and for example, 5 analysis from experimental data. But our task is to find a working combination from a range of 20 giga-electron volts to 13 tera-electron volts in all proton nuclei collisions. And this requires extreme amount of computational power. So the simulations took place in the high-performing computing clusters provided by the Wigner data center. And we had 7 nodes with 16-core Intel Skylake CPUs, and each of them with 32 gigabytes of RAM. And we can see some of the outputs of the Hydrogen++ in combination with the Rivet tools that it helped to generate. And we have 5 terabytes of disk space, and in almost a year, so when I joined, this is the calculation that I took, we made around 22,000 Hydrogen++ runs and created, this is a very low estimate, but 340 terabytes of data. But it can be, I think around, it's more like 600. This is a very low estimate in around half a year CPU time, and this is still not enough. So the tuning is still ongoing as we speak. There are a number of runs that are ongoing as we speak. So in the next slides, I'm going to introduce you to the tools and the tuning process and what you're taking. And so let's talk about the tuning process. First, we setting up the environment. I'm going to talk about each of them briefly, but there's a different slide for every one of them. So first, we're going to set up the environment and going to sample this parameter space that we chose. And after that, we're going to run Hydrogen++ for each of the parameters. I'm going to optimize these parameters and run a validation and see if it's the expected. And if it's really good and all of our analysis is matching the experimental data, then we are happy and we exit the loop. But we stuck kind of here in this never-ending loop. So yeah. Okay. And so I'm going to talk about how we set up the project or the environment for the collision, for the simulations. And first, we have to choose the energy and the collision system and the experimental reference data. So after we've done that, we're going to figure out the most relevant parameters for each simulation and for this set of parameters. And less parameters equals less runs for us because we are not doing a brute force algorithm. So there is a tool that's helping us, which is called Professor. And I'm going to go back one slide. Professor is a parameterization-based tuning tool. So the more parameters we're going to give him, the more runs we have to make, and it's one sample can take days or weeks to run. So it's quite an important aspect to just choose the the more important parameters. And there's also the river toolkit that we're using. It's a set of experimental data analysis, and it's another tool that we just pipe our hygiene output into, and we can get some nice YODA files, which are core of the river toolkit. It's basically a better histogramming tool, and of course we're using the hygiene plus to run the simulations. So after we've done after we figure out the relevant parameters, we have to find a good sampling range for each of them. And this can be quite tricky, because if we randomly choose a sampling range, then one parameter can be very sensitive, and all the runs can be like nonsense, and we have to depend on previous runs or some physical parameters, which we discuss. Yeah. So after that, we're gonna write some scripts to run the Monte Carlo event generators, and we're going to do an example at 5 teraelectron volts with the lead collisions and with this rivet analysis, which is going to be the charged particle, cellular rapidity, density, and sensitivity classes. And we're going to do a little bit of tunings ourselves. So after we've done after we choose the parameters, we're going to sample the parameter space, which is done by the professor. And we're gonna end up with different configuration for the Heinrich++ in each subdirectory, and we're gonna run the hygiene with the rivet. So this is like the run command, and after we run the hygiene++ with for each subdirectory, we end up with a format like this with our outputs. And depending on the sample size, it can take days or weeks to run a sample, and after that we can run the professor's optimization tool, which will give us the resulting directory, which contains the predictions for the generator and the results. So there are lots of intermediate steps involved. So we're gonna make a parameter interpolations, and we're gonna run a sensitivity plot to see which parameters are more sensitive, and so it's quite a lot of tasks. And finally, we call the professor tune, which gonna give us this with a weight file. So with the weight file, we can specify which experimental data is important for us, and we can tune the professor tune to tune the experimental data. So it's quite tricky, but we have to do that. And after that, we try to find the best fit and continue with that parameter set. So this is like the output. So this is what the professor gave us for their predictions, and this is the outputs of the professor. This is just basically a text file with the minimization results and the parameters that it's concluded on. So I'm going to show you another tool that is currently developed, which is a machine learning based optimization tool. It's quite similar to the professor, which is a per beam model, and it uses a feed-forward neural network for each bin, and it's training it with a gradient-based algorithm, and it can use the same sample as the professor, so it's quite good. The tuning step is also the same. It's to minimize this chi-square function, and it's going to end up with our results. So I'm going to show you the validations and the comparison of the two optimization tool. So, so for reminder, there's the energy that we use, the system, and the analysis that we tuned to, and you can later see the experimental analysis on the HAB data. It's public. So we had 6 parameters within these ranges, and the professor is it's quite not quite equal. So there are like some of the parameters that they are quite close, but this is, and we know that this is a very sensitive parameter, and it's quite quite different. So we expect a very different results from this, and we can see that the professor and the found 2 of the upper bounds of the ranges. So maybe we have to recalibrate and do this run all over again with different ranges. So after this, we run the hygiene plus with the given parameters, which the MCNN tunes and the professor gave us. So with the black dots, you can see the reference data, and with the blue line, you can see the professor, and with the red line, you can see the MCNN, the machine learning based tools prediction, and you can see that it's quite not really in touch with the reference data. That is because maybe it needs a lot more data to train, and the professor's prediction is not quite good as well. So this is where we stuck in. So in summary, in the validation runs are in favor of the professor, but it seems that the MCNN tunes needs more data, and we have to do this all over again to do this, to maybe have better results. And MCNN tunes is other drawback that it's a machine learning based tool, so it needs a lot of training, and it's a bit slow. It's quite slower than the professor. The MCNN tunes it was for me around 3 hours to optimize. Professor was like 10 minutes on a CPU, but the hardware probably can take care of this problem. So currently the hygiene plus is in this state, and hope it's going to release soon. So stay tuned. Thank you for your attention, and special thanks to the Wigner GPU Laboratory and Wigner Data Center for providing us with the hardware and the support.
Okay, thank you very much for that. And for questions? Yeah, please.
Well, there's absolutely no guarantee that there is one local minimum for the chi-square, so you can find different local minima.
Yeah, sure.
One check is, of course, what you can do. You can just run the professor around the solution of the other methods, whether it will reproduce it or not.
It's more weighted. So
yeah.
So
but
what
at least you have you can compare the professor minimal chi-square with the one around the solution for professors at the public, because otherwise you cannot compare the 2 methods.
Can you go back one?
Yeah, sure. Where?
More. Yeah. So no, to the table. So what the funny thing is that sometimes you can have much more better agreement with the data, but then you are out of these ranges, or even like here you are reaching the one of the side, one of the limits, which is unreal. So the point is what we are trying to do to find the proper minimums in order to have a good values within the ranges. And in global, it's quite good. In certain cases, it's not the best. Say, but yeah. So we tried many things. It's not an easy task. So I mean, I just want to highlight that the tuning particle Monte Carlo generator used to take like 20-30 years. So it's not a big deal, but we reached this point in 5. So we are pretty good. Okay. Further questions or comments? I just want to ask something that do we still have this 140 terabyte data, or you just use on the fly?
No, it's used on the fly.
Okay.
But there are like sometimes writes to the disk because some analysis needs the other data. So sometimes we just get rid of it. But yeah.
No, that's the normal way, but I just wondering whether we can have this from other people. So,
No,
okay.
no, we can't, unfortunately.
Anything else from the audience? If not, let's thank Balázs again. Last but not least, Tamás Hegedűs, AlphaFold2 transmembrane protein structure prediction.
Actually, I have 2 versions of yours. I uploaded both. I do not know which the right one. Okay. So maybe check on in the collator and then tell me which was the proper one. Nincs rajta? Üres. Ja.
Thank you very much for the invitation.
Please stay there because you are in the.
Yes.
Sorry.
Thank you very much for the invitation. And today I would like to talk a little bit about some biological problem associated with some computational problems. We do both experiments and computations, and most of our targets are transmembrane proteins. No, it doesn't. Are transmembrane proteins. So most of them are transmembrane proteins sitting in the cell membrane and use the energy from ATP to transport several different types of molecules like hormones. And some of them takes part in recognition of toxic molecules, so they defend our cells have harmful molecules. And they are transmembrane proteins, so they are sitting in a lipid bilayer. And what is very important, that a significant portion of our proteins, approximately 25%, are transmembrane proteins. And if you go to the drugstore, then most of the drugs on the shelf are targeting transmembrane proteins. And in order to design drugs for curing some disease where the transmembrane protein is working inappropriately, you should have the structure of the protein at the atomic level. However, transmembrane proteins resist to structure determination. In the PDB structure database, there are over 100,000 experimentally sourced structures, but only less than 6,000 is for transmembrane proteins. A couple of years ago, Anfinsen proved that the sequence of the protein determines its structure. So we have 20 letters, 20 amino acids. We have very long words, and these determines the structure, the functional form of the protein. That was an experimental proof worth for a Nobel Prize. And from that time, computational biologists or computational scientists try to figure out how to predict the structure based on sequence. And that was really a hard problem. And actually, even a few years ago, we thought it will not be solved in a decade or more. But 2 years ago, a company of Google, DeepMind, appeared in the structured prediction competitions with a deep learning model. And this deep learning model became the best 2 years ago, and the model was released this summer. And this model basically takes 3 different parts. The first part is generating the input for the deep learning models, and they use the input structures of proteins which are homologous to our target sequence. I think it is relatively trivial. I think it's relatively trivial to imagine that if you have a structure which has a sequence very similar to your target sequence, that you can gain information from it, which amino acids might be close to each other. However, the other input, which is the sequence alignment of sequences which are homologous to your target sequence. And I have to tell you that it seems that this input has a much higher weight compared to the input structures. And in the next figure, I will explain how the information from the sequence alignment can provide information for the three-dimensional structure.
It's resource.
I think everything is tired at the end of the day.
No, this is not the first step.
Oh.
We do not know the reason.
Yes, from before.
Sorry.
It's okay. So you have a sequence alignment of homologous proteins, and if you observe that at one position a large amino acid is maintained, replaced to smaller amino acids, and you observe at the same time that another position, a smaller amino acid is replaced to a larger one, so the opposite, I might have mixed, then you can make the inference that these positions are close to each other in space, since if there is a larger amino acid at one position, but you don't replace the other one, they will clash. So basically, the central block, the deep learning module of AlphaFold, extract this information, distance information from the sequence alignment. They use transformers with attention mechanism and a couple of small tuning. And at the end, what they do, that you collected a lot of distance pairs between amino acids, and this can be used to build a three-dimensional structure. You constrain the distances between pairwise amino acids with these distances, and you will have a three-dimensional structure. You will not have 5, since they train the 5 different models. They also developed scoring functions, not scoring functions, scores, to tell something about the quality of the prediction. They use the so-called PLDDT score, so predicted local distance dissimilarity test. And if it is high, then the prediction is good. If it's low, probably it's not so good. And first, I will talk about the hardware background for this calculation, since it's pretty interesting. So the sequence searches to generate the alignments, I think it is the bottleneck. Not the disk space which is required. It's relatively large, but nowadays it's not a problem. However, it's I/O heavy. So it's difficult to say, but let's say if your protein sequence is 1000 amino acid, which is not very large, it can go higher. This part can take 7-8 hours calculations. Some folks try to shrink the required database to smaller and keep it in the RAM, the memory. That might help, but you may lose precision because of the smaller database you use. I think it will be okay, just it's still difficult to access such a computer.
Sorry, what do you mean on reducing? So what you can, I have no idea what to, what is the not necessary part?
In the database, in the sequence database, you have almost 300 millions of sequences. And you already shrink these to have a 3 terabyte or 3 terabyte database. But they say if we decrease the number of the sequences, we still will have good alignment. In the alignment, usually I would say we don't have more than 10,000 sequences. And the quality means that if you can collect from the sequence database a good set of sequences of the prediction. It's also very interesting that I haven't checked that shallow alignments, 1-200 sequences might be enough. And that one can be selected from a much smaller sequence database. But it wasn't tested rigorously at this moment. But I think it will work. But okay, DeepMind also told that they used a computer with 85 gigabyte RAMs. I think that is really needed. On the other hand, if you have a very conserved sequence and you collect a lot of sequences, then you might have a problem, since the output of the sequence alignment is, the result is a file on the disk, and it has to be parsed. But if it's too large and it is parsed in the memory, then you are in a big problem. Yes, you have to correct the code. The second part, the running of the deep learning model, of course, you need a GPU. And for this, you also need some higher-end GPUs. It might be possible, I mean, most likely possible to use multi-GPUs. I haven't tested yet, since at this moment, this memory was sufficient for me. On the other hand, I also ran into a problem in some of my simulations stopped with the error caused by TensorFlow. It has a hard-coded limit for a certain data object, 2 GB, and fortunately, it was a bug in the AlphaFold code. As a biologist, I'm pretty proud to find that spot and insert 2 small quotes of line and eliminate this problem, and that was already included in the last release. So generally, I would say that AlphaFold, DeepMind released not only the AlphaFold code, but they also released the prediction of protein structures for proteins of 22 organisms. This is over 300,000 structures. And DeepMind plans to release the structure for all proteins in 2-3 months, which means millions of protein structures. This really will change the paradigm of structural biology, not only computational, but also experimental, drug design, etc. But now I turn a little bit to biology. As I mentioned, membrane proteins, transmembrane proteins resist to both experimental and computational methods. And AlphaFold was not tuned for transmembrane proteins. They were part of the training set, I mean, some of them, but no special attention. So it's a big question whether the transmembrane protein prediction by AlphaFold is good or not. So first, you can take the structures deposited by DeepMind. You can select the transmembrane proteins. You can select the soluble proteins and check the distribution of the PLDT score, the quality score. And PLDT scores higher than 70 can be considered as good predictions. So as you see, similar amount of structures, similar percentage of structures of membrane proteins were predicted as good as soluble proteins. However, it's very important to know that this is just a score, and it also could happen that AlphaFold folds the protein, the membrane protein in a manner which is globular, but the hydrophobic parts are inside the protein, and the prediction score is good. So you want to get a picture whether the AlphaFold predicted structures look like a membrane protein. And you can see the transmembrane helices, and if you place transmembrane helices next to each other, then the ends should be parallel at a certain level. And if you calculate the distance between the two ends, the set of the two ends, the distance of center of mass at the extracellular and intracellular end, then it should be somewhere 20-30 amino acid because the hydrophobic region of a general membrane is so thick. And of course, if the prediction is wrong, for example, one of the helices is not inserted, then the center of mass in this case just get very close to each other, the distance. And we calculated first the distances for experimental structures, and they really fit between 20 and 35 angstrom. And as you see, for the AlphaFold predicted structures, most of the structures exhibit orientation of helices, which corresponds to a membrane bilayer or something like that. You might notice that here is a significant portion of predictions which seems to be not good. However, most likely one portion of this portion is really a good really a bad AlphaFold prediction. On the other hand, I also have to note that we don't exactly know the location of the membrane lipid molecules around the protein. It's also a prediction. And it also could happen that in some of these cases, we couldn't predict the location of the transmembrane helices, but the AlphaFold prediction was good. This is somewhere a higher resolution information on the structure, but we still don't know how accurately the alpha helices are located next to each other in the protein. And therefore, we took a couple of transmembrane folds, transmembrane structures from our ABC proteins. It's a very diverse family. You can see that 8 very different folds exist in this family. And you can take all the ABC protein structures from the AlphaFold predictions, and you can compare each of the structures to every these experimental folds. You could calculate root mean square deviation, but there is a better score in the template modeling score, which can take values from 0 to 1. And if the value is above 0.5, that the two folds can be considered the same. If the value is below 0.3, then they folded differently. As you see, all of the AlphaFold predicted structures seem to, ABC protein structures seems to have good fold. However, this is not a real proof that AlphaFold works well, since, first of all, these structures and almost all of these structures were in the training set. Second, even if they were not in this training set, since their structure, let's say, was determined after 1918, April of 18. So on the other hand, when they deposited the predicted structure and when they predicted the structure, they also used available templates, even from 2020. So it's very difficult. I mean, you cannot judge the efficiency of AlphaFold on transmembrane proteins, also not on soluble proteins. But if you look for structures which haven't been determined before 18, or a similar protein structure were not determined, then you can use that protein for testing the AlphaFold. Tell you the truth, we found only 3 proteins, 3 structures, which have never seen by AlphaFold. 2 of them were predicted very well, just like the experimental structure. And this one exhibited some problem. And the model looked like this. You could claim that the protein is flexible and this is a different conformation, but if you look, the protein is colored from blue to red from the N-terminal to the C-terminal end, and the N-terminus is on that side, while in the other protein is this side, and it cannot happen. The membrane topology should be correct. Hydrophobic regions cannot really cross the membrane. So what we did, we just performed the experiment as long as we got the right structure. So several times with different random seeds. And here you see the PM score. Basically, all the predictions exhibited relatively high PM score, so not really below 0.5, but exhibited a couple of pretty high PLDDT score. Because since this is just one protein, I cannot state that don't use model 5, out of the 5 deep learning models for transmembrane proteins, but I'm getting suspicious. On the other hand, what is very important, the red dots and numbers indicate the top score the predictions from each run. So each run you get 5 structures, one of the top prediction colored red, and from 6 runs, from 6 top ones, there is one which basically exhibit the very same structure. And I think I'm over the time, isn't it? Still, you know, I was written to have 40 minutes, but I don't plan. So usually our main objective is to characterize how the drugs get into the protein, the pathway inside the cell, and how they are transported to the extracellular part. For this, we perform molecular dynamics simulations. And in the last year, we studied a protein from a plant, no structure, but I have built a lot of homology model based on homologous protein structures and sequences. So I also use the homology model for this study. On the other hand, this is already the AlphaFold structure, and this is the AlphaFold structure and the homology model overlaid. And the big problem we had that our homology model was not stable in simulation. This is characterized by the root mean square deviation from the initial structure. It was pretty high for the homology model, pretty low for the AlphaFold model. Actually, this is not so bad, but our main problem was that here in the middle, at the central drug binding pocket, one of the alpha helices got unfolded in the homology model, while it remained stable in the AlphaFold model. And the spheres shows that basically the location of the amino acids were good, no shift in the alignment. So the homology model was great, but the side chain packing was different, and that was enough to provide a stable helix. So we really were surprised that even at atomic level, AlphaFold can outperform other existing methods. So in general, I think that AlphaFold works as good for transmembrane proteins as for soluble proteins. It's very important that people are most interested at this moment in the structure of protein complexes. AlphaFold seem to work for complex modeling also pretty well, since if you imagine that you have a protein with different domains which are interacting in the learning set, that it's intramolecular interactions between different parts of the protein, then this is very similar than interactions between different proteins. However, DeepMind also trained a specific model for complex structure prediction. It was released not this Tuesday, last Tuesday, but they are doing pretty fast. There are also some drawbacks. The conformation is random. What does it mean? If I have 2 different conformations for the transport, open inside to the cell, so the substrate can bind, then ATP change the conformation, and you see it's open to outside. And we don't know how AlphaFold produce which conformation. Sometimes I would need the outward open conformation, but I just get the inward open conformation. Yes, I haven't tried the AlphaFold multimer, but I'm pretty sure that I will run into memory problems, and I really don't like. I mean, I was pretty surprised. First of all, they had some bugs, and pretty important bugs. on the other hand, it was just so good to read their code compared to the code of other scientists. People like to say and state that the protein folding problem is solved. Protein folding is you have the straight peptide chain and you fold it to the three-dimensional structure. I would like to emphasize that not the folding problem is solved, but the structure prediction based on sequence. At this moment, we still don't know the important steps of the folding, which are very, very important in certain diseases. But I think that AlphaFold also helps in this. Okay, I really thankful to my group, to Gina and Bianca. But at least Gina just delivered a baby in April, and they made some fancies. They called the girl Regina, so Regina. Bianca got married 2-3 weeks ago. So, but hopefully now I have new computational colleagues and we will advance. And I really would like to emphasize that I got a lot of help and input from a lot of computational people, hardware and ideas from Gergely group, and also from another ones like Max Planck Institute, and also sometimes Kifu helps me a lot. But of course, the current cluster cannot be used for this, but as you heard in the morning, hopefully the next one will be really powerful. Thank you very much for your attention. If you have time that we can have some questions answered.
Thank you very much. Sometimes, and the computer just died in the very last minute. So anybody have questions?
I have to know that, you know.
Oh,
It should be verified questions.
What's in your no?
You showed some movie, some dynamics of done some like dynamics. But so that is not, so the change of the structure of the protein is not calculated by AlphaFold. No. This is just some extra work. Once you have the structure static, then you do some.
Yes, exactly. So it also could be an interesting question. People already asked me whether we can produce a conformation ensemble with AlphaFold. At this moment, I don't think so. Even if you want to have a different conformation, we cannot have it. For example, I tried to build a structured database which can be used for templates, and it contained only a specific conformation of my protein of interest. And we still produce the other conformation. Therefore, I can state that not the structural input is the most determinant. Out of the 5 models, I think there were 2 which were trained only at the very, very beginning with structures, and all the other training steps and improvements were using only sequence alignments.
Further remarks or questions? If not, so let's thank so much. We are at the end of today. Thank you very much for your cover. You pushed this event today. Tomorrow we will meet at 9, and then we will go until lunchtime. And at the lunchtime we will switch over the GPU day to the AIME with the new opening and to turn to this quantum phase. And tomorrow is mostly dedicated to machine learning, quantum computer simulations. So we welcome if you can join us, either real or online. So thank you very much. See you tomorrow.
Köszönjük!